Okay, hello everyone for the third day of Glasgow School 2026. So here we will do some magic with Fortran today. So a bit of OpenSCC, a bit of OpenMP, stuff like this. So I will not spoil everything because of course that's a bit of a surprise. So after that, we will have a quick visit of the LAPP museum for those who attend the school in Annecy. And then we'll move out also to the next part of your presentation on Fortran and the lecture on Fortran. And then we'll finish with some memory management and memory profiling tricks at the end of the day. So Vincent, it's up to you.
Good morning, Fortran. Make some noise for the oldest language. So I am Vincent Lafèche from IDC Lab in Orsay, and the very happy teacher of this part of the lecture. So Fortran is known to be old. Some quick show of hand who has ever practiced to some extent Fortran? Okay, so modern Fortran? The same. Okay, very well. It all started in 1954 with a project that wouldn't stop. The idea was talking to computer was the tedious talk. So if non-expert already at the time had some way to express things at a higher level, and in IBM, they started the automatic coding system for the IBM 704. It was presented some 6 months later and delivered in the spring. The meaning of the name is formula translator. It is handling the first abstraction, an abstraction that is so common that we don't think about it. It's a so-called expression abstraction. When you talk to a CPU, you usually move things one by one. Add this to this, multiply this to this. But our brain is capable of much more, and we express long formula, and we would like to avoid the tedious part of translating it to the compiler. And we know that mathematically, at least, there are multiple ways to translate one given formula. Some of them optimal, some not. So the job of the compiler in this respect was really important. It transforms expression into an evaluation tree and possibly the best one. So Fortran is not the oldest compiler, but it's the oldest surviving compiler. The language that were older than Fortran didn't make it. And in any case, the oldest standing. So what is more important is that it's the oldest compiling optimizing compiler. And it started with fixed format, with punch card. So it's very computation oriented. It's not system oriented. And this is what makes it a high-level language, which is not some value statement, but rather expressing the fact that it is an abstract related to the memory model. When I say C is a low-level language, it's not deprecating. A few types existed at the time. So floating points, and we will see tomorrow that even if it means very definite things today, at the time it was rather wild. Integer, the base of the base. Logical, and even character, and some very archaic strings called the O'Leary's string. So this guy, John Backus, the father of Fortran, didn't stop with Fortran. He started with Fortran. He won the during award 77, because after Fortran, he realized the flow of the design, the lack of the generic notation to parse. The parsing of old Fortran is a nightmare. And he wrote about functional language on his contribution to the parsing community with the BNF notation for all more modern language. So at the time, 95% of the people who programmed would never have done it without Fortran. So this was really massive. It was the language introducing people to computing. So the history went on the following point. The first American standardization was in '66. We call it Paleo Fortran. 68 already mentioned the author of BASIC that was 1 year old at the time told about Fortran as old-fashioned. In '68, I was not even born. In '77, the influence of structural programming in the '70s led to Fortran 77, so-called Archeo-Fortran, a bit better. And it was very influenced by the procedural paradigm, so another high-level language handling the second abstraction, this time the abstraction of control flow. You could, from Fortran 77, avoid a lot of go-tos. This was the plague. This possibility was not really exploited by practitioners at the time. So this is what will make you bleed when you meet this kind of old code. In 88, there was a missed opportunity for Fortran 66, Fortran 77, Fortran 88. But IBM and the other industrial partner of the Fortran committee did not settle on the version, and so it had to wait for 3 more years with Fortran 90. And this time, we are handling the third abstraction, which is data abstraction. So most of you have been exposed to object-oriented programming. A large part of object-oriented programming exists before inheritance. It's so-called object by composition and not object by inheritance. And this abstraction is really useful, defining derived type, the equivalent of structure and record, trying to escape the bane of common in Archeo-Fortran. What is more important is, what is as important is in '89, you had the first open source, not compiler, but translator from Fortran to C, and as there is always some C compiler on any good Unix machine, there was not much difficulty. The first free open source compiler was in '95. In '95 was the name of Fortran with dynamic allocation, something that people used to see at the time were very much, with reason, reproaching Fortran. Then Fortran 95 got his own first open source compiler in the early 2000s, and this G95 compiler got introduced into the GCC collection. And all along this history, you will find papers on top of papers telling Fortran is dead. Fortran has no future. It has been so for more than 70 years. So Michael Metcalf from CERN is a strong proponent and activist for Fortran, and he has been pushing Fortran 90, but this window of opportunity of 3 years that was missed was something that made the community in physics change rather to C++ than to Fortran 90. Nevertheless, as Bernd Strustrup says, there are only 2 kinds of language, the one people complain about it and the one nobody uses. There are a lot of complaints about Fortran, so it exists. In time, you can see the usage on the Archer 2 supercomputer in Britain, I guess, where you see that for explicitly defined as Fortran project on this supercomputer as almost 2/3 Fortran. But in the unknown part, there is certainly some contribution of Fortran as well. So we have really a large part, and Fortran is not pushing up the daisies. So to get some synoptic history, I don't see it would be better. Okay, so no pointer. So on the top left of this diagram, you see the place where Fortran started. It started with the so-called procedural paradigm, which really took a step further in 1977 with else in the if, and if, and do while, so typically procedural things, and in Fortran 90, select case, the equivalent of a switch. But the last important part of the procedural paradigm appeared with Fortran 2008. Because what you want in procedural paradigm is to isolate a snippet of code in the middle of your function and make a new function from it. And to, it displays nowhere. Ooh. So it does not display here. No, so I see my slide here, but not here. It's not responding. Il me dit qu'il passe en suspend. La souris marche pas.
C'est vrai que je vais dire qu'on est en 2 minutes.
Ok.
Autant qu'on fasse ça. Tu peux l'annoncer?
Sorry for a technical break for 2 minutes, please.
c'est mal pris. Il a bien pris.
T'as un bidule, tu veux un bidule pour passer les slides ou...
De l'autre côté. Ouais, mais je vais pointer avec le.
Ouais,
avec
sur
la
la souris, c'est mieux parce qu'après...
Quand elle marche. Ouais, ça marche. OK.
On est en ligne.
Elle est beaucoup moins chaude.
Welcome back after a short heat wave on the GPU on the corresponding problem. So we were addressing the synoptic history of this venerable language. And as it started with procedural, we directly go to the next level of abstraction, which is modular paradigm. Modular paradigm existed in some respect in old Fortran. You could do object programming in singular. With one command, you have one struct of only one object. So when you speak of object-oriented programming, you mean, in fact, class-oriented programming. In the oldest Fortran, you could program with one object at a time. So now people really use this kind of concept, and it's a bit overextending the definition. So common are the plague of old Fortran, because it has never been used right. And it was completed in 1977 with include, which allows sensible people to not define and copy the same command in each routine, including it. So for people not used to common, it's a common area of memory that allows you to share variables, arrays, and so on between different functions. It's an extended scope variable. It's a global variable. So from a computer science point of view, it's really something you don't want to see. And in fact, much older Fortran has this problem. So it was properly corrected with Fortran 90 module on type. So variables defined in a command are global to this command, and types allows you to have multiple objects of the same type, then entering the realm of object-oriented programming. And it was completed in 2003 with extends, which is the word for deriving, inheriting classes from one another. So Fortran 90 introduced a bunch of important words for dynamic allocation, dynamic programming. You have pointer in modern Fortran, and they are used sparsely. You don't want to use them for anything like in C or C++. We'll see some usage in the code today. In Fortran, you cannot have a pointer to anything. You can only have a pointer to some target variable. So you need to define a lot more things. And there is also allocated variable. The difference between pointer and allocatable is subtle. The variable, the allocatable variable has a lifespan of its compilation unit. If it is in some module, it will exist from the first time the module is invoked to the last time. If it is defined in a function, it will disappear at the end of the function. There is some automatic freeing of allocatable variable. This is not the case for pointer. You have to free them explicitly to unallocate them. And then we enter a really interesting programming paradigm. So Fortran is not really a functional language, but in the sense of functional paradigm language. But from the early Fortran, you could pass functions to a function. You could pass subprogram argument. And something that was very much snorted on Fortran was the lack of recursivity in the declaration. So any compiler needs recursivity to address expression with an indefinite depth. So the early Fortran compiler had recursivity, but did not provide recursivity to the user of the language. So this was also solved with Fortran 90 recursive statement. Another functional aspect is we didn't need the pointer in Fortran because everything was passed by reference. So you don't write star or ampersand, and your variable is not copied. This is powerful, and this is risky. So Fortran 90 introduced the intent. When you declare some function, you provide intent to each of the arguments. Fortran 95 introduced two very important things, particularly for concurrent programming: pure functions and elemental function. Okay, so we have seen today before what is a pure function, and then you can state this function that I declare to you, compiler, I tell you it is pure, and the compiler will check the minimum level. It calls only pure function, and it has no explicit side effect, no write in particular, or no read. It doesn't modify any external variable. If you try to modify some value in another module, the compiler complains. And yes, in a function, all the parameters should be in. And okay, you can have in-out parameters in subroutines so that you can pass back value. Elemental means, in fact, elemental pure. So it's a kind of auto-mapping function. As soon as your function is pure, if you apply it to A and then to B, the result is for the opposite ordering is strictly the same. If you apply it to B and to A, you would get the same result in a different order. Starting from here, you can express concurrency. And then you can, if you want to apply your function to an array of value, the elemental function allows you to avoid writing the loop on the array. So it's very powerful as some way of expressing as far as expressiveness is in play. So starting with Fortran 08, you can have some dirty mix of both, which is impure elemental subroutines. So sometimes you want to display an array, or you don't want to write the loops. So you tell your compiler, the routine that will do this will be some impure elemental. There are input-output, so it's not pure. But, okay, come on, write the loop for me over this array. I pass you the array and not each value in turn, and do something to all the value of this array. So in the future, well, some compiler starts to have Fortran 18 or Fortran 23. We can define simple functions. They are purer than pure. They not only should not modify the environment, but they should not depend on any kind of external value. Concurrent programming builds on top of this. So from Fortran 90, you have array expression. In 95, you had the first attempt at std for each loop more powerful than array expression. We'll see it. It didn't go well, so it was corrected in Fortran 08 with do concurrent that we will be exploiting in this lecture, as well as the notion of contiguous array, which is very much needed for vectorization. Parallel programming used something which is not proper in the Fortran norm, but which is a sibling normalization that exists also in C and C++. As far as distributed computing is concerned, MPI has been the top contender, and it is slowly and marginally replaceable with co-array Fortran. So we'll take a quick dip about it. And co-array Fortran has been extended to the notion of teams of process in Fortran 18. The missing link in all this rich capability for programming is generic programming. So in Fortran 66 and 77, you could do pre-processing. So you have one routine and you make multiple copies of it, and with some macro, you replace the types in each of the copy. This is dirty, this is efficient. You had the definition of intrinsic function, the one that are provided by the compiler, by the Fortran library in some sense. And in Fortran 90, the notion of interface would allow you to call, which is a polymorphism at the lowest level, to call the same function for multiple types of arguments on return under one name. So it's the lowest level of genericity. It's not full parametric polymorphism that we call for, that will be some kind of template. And it is expected for the next normalization of Fortran. You will see it, you will use it. And in my view, it's what is making Fortran behind most contemporary language, as far as in C++, you want to use object-oriented, but you really want to use the standard template library. This is half of the power of the language for day-to-day programming. So this is what has been missing in Fortran, mostly. So if you want to go into more technical detail, there are two good lectures in Idris, the advanced lecture and the expert lecture. There is also an introductory one. Maybe the link point to the French version, but there is also an English version. So really, you should bug the colleague at Idris so that they call back the colleague that went into retirement and that was doing an excellent job of teaching this subject. So, in the same sense as in the 80s, people would say that basic programming is not basic programming. Fortran programming is not what we expect. So the supposed Fortran style is fixed column format, no indentation. Imagine before 64, it was not even a name indenting the code, because your code would exist with as this kind of cards, and you could have meaningful things from column 7 to column 72, so you were really limited. So the normalization introduced only 6 characters per variable or function name. So it's difficult to be expressive with this. Very dirty aspect that we are keeping today is the implicit typing. Variables starting from A to H, A to G. A to H, are integer, and above n, they are integer as well. They are real as well, and only from I to n, they were declared, if you don't do anything else, as intrinsically integer. Okay, A to H, real, I to n, integer, and you have lots of old code that rely on this, and it is very tedious to debug. Hopefully, we have tools, and half of the life of a Fortran programmer is not writing new code, but keeping up with the code of ancestors. You would repeat declaration on commands in each function that would use it. It had two long functions, so I have seen a 9,500 line subroutine one time. Okay, so we are far from software engineering. And okay, the dreaded goto overuse, arithmetic goto are really wonderful, and it led to a lot of spaghetti code. But when you look at the modern Fortran program structure, you must accommodate the old one as well as introduce new things. So you always have a main program, but you can name it something else than main. So please put a meaningful name. This main program will use module, so use in the sense of import. In your module, you have data hiding, so there is a public part and a private part. In each of them, you have data, and you have internal some subroutines or program then that can in turn contain one more layer of internal subroutine. So you can have a module with one subroutine, including one subroutine, no more, no deeper layer. So this is the modern way of using Fortran, but you must accommodate the tons of library that are defined without the benefit of module. And so you can call subprogram. In this aspect, it will be a hard job for the linker. The linker will have to fetch things. And what we want to do more and more in modern versions of Fortran is to provide the compiler with the maximum information so that it can optimize and check things better. For instance, I will not address this in detail, but it's a nice way to proceed in the future. Nowadays, you can have sub-modules. So a module can be very extended, and you don't want to recompile. It is a compilation unit, so if you modify one line, you will have to recompile the whole module. So starting from Fortran 2008, there is a notion of submodule that allows you to define only the kind of header part in the module and have a different file containing one or more functions of your module that will be called submodule. This is very good to avoid code duplication and to avoid the hassle of recompiling large modules. Okay, so the answer is in the title, no. Not all Fortran is legacy, but we have a lot of legacy Fortran to deal with. You can consider that, in general, legacy code is code that you have not written yourself. But in particular, in this context, it means code of Jurassic Fortran, Paléo-Fortran, Archéo-Fortran, and also some Fortran 90 starts to be dated. It depends very much on the author. So if you want to move your old Fortran library to modern one, it's not simply converting to free format. It's a good thing. So you have the program of Metcalfe, the one I named with the link that you can follow here and here. It's not always easy to compile this convert.f90, but it does some job of converting only the format. But going to modern Fortran is really an opportunity to turbocharge your code for expressivity, resilience, and clarity. And we have this tool, SPAG, from Polyhedron Software. So you have the link to this company. So SPAG is a commercial product, but for the academics, you can have it run for free on Linux on any kind of project. So if you have code that makes your eye bleed from Jurassic Fortran, have a SPAG simplify it in this way. So you see on your left the old expression, on your right was SPAG has made of it. So you have only block if, else, and if, and not this horrible arithmetic goto. It's a bit excessive what they did. I have never seen that amount of arithmetic goto in so few lines. But okay, we prefer to read what is on the right side. For 2 years and a half, you can have for free the most recent version of SPAG that also turns your common variable. So you see here you have some function with global variables in the store, in the common EG1, N, L, and down. So we have implicit typing, so N and L are by default integers, and down has been explicitly declared as integer. So SPAG turns your code into implicit none. So if you have not done it yet, this is the first line you type in any serious modern Fortran. Then SPAG also introduced private variables. So here, only the variable of the common that have been translated in this module are considered public. Okay. And I don't know how it got renamed, but why not? So two good things, implicit none and private. This is modernizing your code. Okay. So I've been using SPAG for 27 years. It has always done a great job of converting the code. Don't start with a 10,000 line library. Start with program you can have some confidence with. But I've not met problem in 27 years. So you have a lot of configuration capability with SPAG. You can only beautify, you can relabel, because as you have seen here, old Fortran was characterized by a lot of label on the line. So you had to think in advance the numbering, and when you were modifying your code, it was a mess. You would be able, depending on the value of some variable, to go to a different line. So not good at all. On restructure, so beyond relabeling, and there is also some kind of dynamic analysis, but this must be in the version that you pay for, dynamic analysis. Okay, so this is only a short excerpt of the configuration capability. You can pilot the number of spaces before parentheses, after some level of parentheses. Okay, so now let's define some recipe to deal with old code when you want to modernize it. first thing first, some researcher comes to you with Fortran 77 code, you put it in some version control system. It usually comes without. It has been passed from floppy disk to hard drive over generation, put it in the right context. Then have any kind of build system. So many times it comes without build system. When you are lucky, the researcher knows a file, kind of shell file, where there is a command that compiles your program with some obscure option, minimalistic. So put it in some right modern format. Then if it's fixed form Fortran, you should pass the old linter FTN check. So it is also more than 30 years old, probably 40. Compile with warnings. So you will have a lot of them, but should deal with them. Declare everything, either by hand or preferably with the help of SPAG. So you should have implicit known in your code. And if you want to be sure that you have not forgotten one, Fortran has some F implicit known option that asks the compiler to proceed as if every function was implicit known. So in NV Fortran, it is minus M decl check, declaration check. So you should do it as well. Linters exist for old Fortran, but also for modern Fortran, you have a very opinionated fortitude on Camfort. So they will bother you on a fine point of the modern standard. You also have some cyclomatic complexity analysis. So in a large code, in any code, when you enter a function, you have one way. And then whenever you meet some branching, some if, the number of paths through the code will multiply by 2. And so you count any kind of if. It can be the end of a loop as well. And each of these features will add 1 point to your cyclomatic complexity. So if your function has up to 10 points of cyclomatic complexity, it's okay, it's a good function. When you reach 20, you should already consider splitting your function in two. It is okay if in all the functions of your program there is one kind of master control function that will have 26 or something. If you have 600, something has gone wrong. I have seen it. This goes behind the function, but you can proceed to cyclomatic complexity analysis with the Lizard program. You should also check for code duplication, because in the old time, it was so much easier to copy and paste than to do a proper function, that you will see tons of duplication and the error that come with it. Okay, so when you have done all this, you can really start unspaghettifying with SPAG, convert each command to include, possibly with SPAG, and then convert to free format. You can see the paper. Then you convert each include to module to be really modern, and you can do it with SPAG as well. Convert all the static variables that are initialized. Some of them are intended as constant. So here, you cannot make the equivalence that saved variable, static variable, are constant. This is not what I say. But most of the time, data parameter or saved variable were used to define a lot of constant value, physical constant, programming constant. And if they are really constant, then turn them into parameters. You should then declare the intent of all your procedure arguments. So sometimes it's not obvious, but you should aim to have as much as possible intent in argument. Once the intents are declared, then you should declare pure all possible procedure. And afterwards, you should declare elemental all possible pure procedure. Some point we'll also use in the Grayscott Fortran version is to generalize the kind for all floating point variables. So I'm a bit overextending on the aspect of precision tomorrow, but you have obviously the two standard format for floating point, single precision, double precision. Fortran is known in most compilers, JFortran and NV-Fortran. Intel Fortran, I'm not quite sure. Yes. These three have quadruple precision for a lot of details, 33 decimal digits. One precision that is not supported by Intel, where it should be, because they were the proponent of the extended double precision. So you can use it in JFortran. It's not vectorizable, but it's in silico. So it will be faster than quadruple precision. So as engineers should do, you should not define too soon in the project some important aspect of this project. So you want to switch on the spur of the moment between single precision and double precision. If you generalize in the way we'll see the kind parameter, you can have the same program running in simple, double extended, quadruple, and for people who really like to suffer, have precision that is coming to modern Fortran. But I will say bad things about half precision tomorrow. So convert the old do and do loops to either elemental function call or do concurrent loop. So we'll see the limitation of this statement. And if possible, use more appropriate function, because of course, nobody should build his own matrix product. People have been providing library for matrix product for 70 years. Don't do it except the first time you learn in programming. Always use matmule in modern Fortran, dot product, Euclidean norm 2, and transposition of matrix. All this operation provide opportunity for the compiler to optimize it and to parallelize it if you have a recent enough compiler. In JFortran, there is some option that allows you to tell the compiler to use such and such basic linear algebra library. In particular, if you want to switch from classical BLAS to open BLAS to dedicated builder, dedicated maker library. Okay, but Fortran has still not a strong reputation of computer science. So can we have a Fortran unit test? Yes, so NASA produced the F unit in the sense of all these X unit frameworks. But they extended it with a PF unit for parallel Fortran unit test. So these are kind of unit tests that you can run over MPI. So you can use UTF-8 character in your command. So it can help express more things. You should use the intrinsic Fortran env module to define what function in this case. So we'll see also that this kind of blanket statement for use is good when you learn, but you can refine it with the only that allows you to know exactly which function you are invoking in your module. So you recognize the doxygen style comment because you can doxygen your Fortran code. On this part of the unit test is the system under test, the SUT. We want to check that this pure function that will return a list, so an allocatable array of unknown dimension at first, an array that will start with an empty vector. So here, the vector we have, as it is empty, we need at least to provide the type of element it will have. On this short algorithm, we want to test it. So the list of divisor of some integer should not depend on anything but the integer, so intent in, and the result is then pure. And then PF unit has some .pf code, so parallel Fortran unit test, that have this non-standard keyword at test, at assert, that are exploited by the PF unit framework to produce a list of assert in one test. And you can define test in this way. So the Docker image that you will use, you can start downloading it, but yes, I will give you the link. Is compiled with PF unit in case you want to try it. So you can go to some other kata of unit testing on the TDD in this case, test-driven development testing. We also have a function that takes some integer and will return a string. Yes, this is part of the image and the reality of Fortran. Fortran is more thought as an integer language than a string language. There was some meme last year on the Discord to remind us this reality. There are some nice library. Oh, sorry for the small size. The slide will be accessible. So there was, you can not look for regex in a Fortran string with only the default language, but you have library that allows you, yes?
Just a quick stop. If you want to access the slide, they are already online. So
okay.
If you want to pick all the information, it's okay right now.
Okay, so this is the system under test. Here we provide a list in turn of what we expect. We expect that one will provide the string with Roman numeral 1 and so on. And after this test, you are confident that your system is working. And you can extend it. So I invited you to be more expressive. A lot of Fortran code is for computation. A lot of Fortran code has mathematics and physics implied in the name of Latin letters only. We miss the Greek in the identifier. So let's put the Greek on the mass in the comment. And let's use the exponent notation in the comment to make your code more lively, more understandable for physicists and other scientists. So here you see a bunch of standard constants in high energy physics, and not only, and some way that you can present them. Okay, sorry for the size, but we can do object-oriented Fortran since 03 in the sense of a class is a type, okay, with function. So when you declare this kind of type, you can declare some of your methods as final, so they are destructors, and you can have other simple procedures that are then methods. And if you want to build a constructor, you want your constructor to have the name of the test, so you can provide an interface face test to the procedure that you will define as constructor. And so, okay, this is not a very interesting class. I was reminded 2 years ago that should this content of the object be allocatable? As it is allocatable, we really don't need the destructor method. But you can imagine that instead of allocatable, you have a pointer here. And in this case, you want a destructor. And it checks if this array attribute is allocated, then deallocate it at the end of the object. Okay, so you can play the standard display of creating some object of type test that we have just defined inside the block. So you will see on writing this first message, then there will be the message related to calling the constructor. And when your block is ending, you have some message. You can see the destructor at play. You can see destructor work before you see the program end. Some very strong aspect of Fortran 03 was the interoperability with C. You have tons of libraries that are defined in C, and you would like to use without translating them. So you have two levels. So in this case, I took a library for decimal floating point number. Floating point number that are emulated with base 10 instead of base 2, as we will see tomorrow. It has some interest, and you can have, for instance, quadruple precision decimal over 16 bytes. So you declare a kind of blanket structure to get all the data of your DEC 128. And you declare an interface to the various constructor. You can declare how to translate 128 from a real, from an int, or from a string, but each of them should be seen as one specific constructor. You can interface with operators, so it's already true for your Fortran defined code. You You can also define an ordering operator, and you attach them to some C procedure. So the scene binding is this part where you rename in Fortran something that is declared in the C part of the library. But on top of this, you will have so-called SYCL binding, which will make your program more usable. So a bit like we have seen, so you will have constructors, an operator. Okay, so sorry for this. What we call a SYCL binding is something that allows to operate at a higher level, whereas the scene binding that was not properly exemplified on the previous slide was in fact only the way to rename. Okay, so sorry for the mistake. The scene binding is only providing a Fortran name for the conversely defined C function. Okay. We don't have much opportunity to use assembly in Fortran. There is no by default way to do it. So what you would do in C with this 4-line, you cannot do it directly in Fortran, but what you can do is to declare an interface to some function, to some C function that we'll see after, with the name of the corresponding C function that will be translated to this name in Fortran, on where the argument SRC will be passed by value as yes.
So you cannot do inline assembly.
Inline?
Yeah, like
inline it? I have not checked whether it would be inline, but okay. So this would be the C function.
Yeah, that's inline. I mean, otherwise you would just write in an assembly file, right? Yeah. Another question I have now is this going a bit out of scope, but I'm mostly a C programmer. What benefits do Fortran yield over C? Like, for instance, I think it was mentioned that it's able to order mathematical operations, which seems to, at first glance, I mean, yeah, it gives a performance boost, perhaps, but it seems like it's not IEEE compliant in that case. Is it?
It's not
IEEE compliant, like in terms of floating points?
Ah, okay. So IEEE compliance, we'll see some of it tomorrow. I have not read it to the point where it compels you to some order of compilation, to some order of evaluation. It tells you that format are so and so, this is the base level. Then it defines some standard API, and it promises to deliver correct rounding on a limited number of functions. But I would not be so bold as say that it tells us the order of evaluation.
Okay, another question I have is regarding, say, fine-tuning. So, of course, with C, you have more system-level programming. What would you gain or what would you lose by switching to Fortran, like in a more general sense when it comes to fine-tuning?
So we'll see it next week in the talk about vectorization. It's easier to have control on the low-level part, which is needed for vectorization in C, for sure. But elemental function, nice point. expressivity, power, concurrency, all goes in. So if you have this kind of priorities, yes, it's better to go to Fortran. It can be very tedious. Okay, in C, you can have pointers of pointers. This can be really powerful. There is this very good computer 5 video about sorting algorithm with pointers of pointers. When you want to do it in Fortran, it's a mess. Okay, so you have to consider all the balances of the kind of algorithm you have. But we will see some more detailed example today with the Grayscale code to see what is more abstract and what is more tedious.
So one final question. You have, so you essentially, you don't operate on pointers, right? You don't operate on pointers. Like you do allow it, but essentially you operate more on, say, arrays. Is that correct?
Okay, before the end of the day, I will have used the word pointer at least 3 times. So you will see it is useful, but yes, most of the time we operate on arrays.
So in general, you would operate on memory operands that do not overlap, right? Which allows for optimizations. Yeah.
This is something that has contributed to the legend of Fortran, the fame of Fortran for speed and power, because as you can promise that there is no aliasing most of the time. In this respect, it is what made it competitive with C. Is it the answer you expected?
Yeah, thank you.
Okay, so assembly binding is possible, but I have not seen a respectable way to use it until now. Okay, so a lot of things are missing in Fortran. So there is some ISO paper of the early 2020s about languages vulnerability. And after the generic paper on languages vulnerability, you have 15 detailed papers, one of which about vulnerabilities of Fortran. If you want to select some language, please have a look at the vulnerability of the languages you use in these norms. Okay, in principle, ISO norms are expensive, but somehow you find some copy on the internet. It's nice to have a look. Among the missing part of Fortran, we have no multiple inheritance. Some people will tell me that it's not object language because there is not multiple inheritance. So you would replace it with the facade pattern. You have no real first-class function because what you can do with a pointer to function, to external function is not as nice. You have some alternative with a procedure pointer with limited expressivity. You don't have lambda function, but okay, over the last 10 or so years, Fortran has known some kind of fame. It's better advertised and advocated by a lot of people on the net, and they publish a lot of nice papers about how to mimic some kind of lambda expression if you really want it. There is no expression handling, but there are good publications. There is no programming by contract, but you can also mimic the assert. There is no genericity, and we wait. There is this nice GitHub page here that provide example of what should be compilable by Fortran 2020Y. maybe before 2030. But I guess it will take time to enter compilers. The norm is the first problem, but not the only one. We don't have a proper const variable because parameters are more like a const eval or const expr, static const expr of C++. They are defined at the end, at the start of the program, at the compilation even. And so you cannot define your own const expr function that you could use to define at compile time some value. So even such simple thing as a constant have in fact a very broad meaning depending on which language you say. It's a kind of define like C in the sense that a define is replaced and doesn't lead to a symbol in the compilation object. So the parameter, except for parameter array that are also rather recent, a parameter constant will not lead to a symbol. It will be replaced, hard-coded into your code. But contrary to a define, it has a type. So the compiler could do something about this value, could check that it is proper. So as we don't have this const, in fact, when we pass argument with intent in, or when we have a protected value in a module, so protected means it's private with respect to writing, but it's public as you can read the value. There is no variadic function. So when you want to bind to some C library, you have to make multiple binding for one variadic function, and you have to know in advance what extent of variadic function you want to use. So this is a bit tedious. Okay, and there are no coroutine. Okay, so this about the detail of the syntax is not very interesting, and we move to harnessing the power of array. So we want to get rid of not useless loops, but loops that doesn't bring clarity to the expression of code. So, okay, with MATLAB was written in old Fortran at first. And MATLAB introduced a lot of such array operation. You could sum two arrays, you could multiply two arrays and so on. You could apply the element-wise operation. In particular, the element-wise product is the Hadamard product, which is the trademark of this school. And so modern Fortran took the inspiration back from MATLAB with mapping intrinsic function as elemental and allowing the user to have his own elemental functions. You have array reductions such as sum and product. You have dot product, you have matrix multiplication, and you have reshape. So, contrary to C++ that is just discovering the multidimensional arrays, Fortran has it since 57. And sometime you want to see your bunch of data as an array of some rank. Maybe you have defined a linear collection of data, which in fact is some matrix. So rank 2 array. You will do it with reshape. Reshape doesn't copy anything. It doesn't change the data. It doesn't move them. It just provides you some way to look at the data with some other ordering, but some other, not ordering, some other shape. Okay, so you have also where clause that operate with mask on your collection of data. When you can, when the loop that you want to execute on some set of data does not depend on the order. 20 years before, you would have used for all, but now we use do concurrent. So what difference between these three ways of expressing something? Okay, arrays are very concise, but sometimes you need to put something in the array that depends on the index. And then array expression does not provide you any way to do it. So you turn to for all loop, but it was so strictly limited that it led to do concurrent loop. So we'll see some example now. And we'll see for all expression of parallelism, we'll turn to do concurrent loop for good and bad reason. Okay, so some example of array expression, you define 4 vectors of size 10, and you can, yes?
Actually, I don't understand why you. Yeah, sorry, the microphone was off. I would like to understand why do concurrent exists when there's also OpenMP parallel fours and things like that.
So as we will see maybe after the break, we have an embarrassment of riches. We can express parallelism in tons of ways in Fortran, on tons of not controversial, but different way. If we want to do it with OpenMP or OpenACC, we need to restrict to do all the do loops. I guess that people decided, in the committee, decided that some compiler may be confused when you had do concurrent on some OpenMP or OpenACC pragma around it. Should it be compiled with the OpenMP statement, OpenMP library, OpenMP framework, or should it be compiled with an internal optimization applicable for do concurrent in the case of this given compiler? We will see about vectorization in Fortran next week. That also at first they forbade to have OpenMP SIMD function defined on top of elemental function. While you would really want it from a moral standpoint, you can't have it. You couldn't have it until 2019, I guess. And they agreed on some way to get rid of this limitation later. So I understand it does not fully answer your question, but you will see more with example and with the practice in next part. So Yes, well, almost not late. Okay, so array expressions are self-explanatory. You can apply elemental function. You can symmetrize some matrix with M plus transpose of M. But if you want to set some diagonal of a matrix to 0, you will use for all. You would have used for all. So you see that compared to a loop, the expression of the range of the index is different. Here, we can also, in the for statement, have some mask next to the range. Do concurrent loop took the same statement of indices on mask, and you can also nest, like you see in this last example, multiple indices, and the compiler will decide in which order the loops should be rolled depending on the data structure. So you are in a high-level language, you provide a lot of ease to the compiler to exploit parallelism, but you do not control the way it is done. So this is the kind of trade-off between C and Fortran. Okay, so you have also the reduction statement for the concurrent loop. You can decide that some variable is in fact the one that will collect the reduction of all your parallel treatment. Okay, so this is only to show that coarrays allow you to have distributed code over multiple processes. We'll shortly talk about it. All these code examples, you will find them in the annex subdirectory of the GitLab that I will pass you. Okay, so when you want to compile MPI or coarray, you usually have to pass tons of compiler flag on specific compiler flag. So be prepared in case you want to do it. Okay, this part will be discussed more in GPU. This part will be discussed in vectorization in Fortran next week. There is some example about vectorizing a cube root that I will discuss on next week. This is some example that we'll discuss in GPU with OpenACC on some CUDA Fortran. And now, for what we'll do after the break, you can find the code, the build with this GitLab link. You have some example of the makefile that has been a bit too much complicated to be able to deal with Intel Fortran, NVIDIA Fortran, and G Fortran. You will find some detail of the setting of the flags using a pkg config depending on your system. I like my makefile to be self-documenting with this make help, so you have tons of check that you can use. Some of them will not run, in particular the word cloud will not run inside the Docker image that we'll provide. What I advise you when you take a new code is to build some word cloud out of it to tell you, is my source code mostly about technical details of the language, or are some names already expressive related to to the finality of this code. So here we see that there is some notion of Laplacian, but we have a lot of PR for precision. So, okay, we have matrices MAT-U and MAT-V. We have stencil. So this code is not completely obscure. Some meaning can turn out of it. Okay, so no need to enter the detail of the makefile. Okay, we'll discuss this part after the break. So we are back in half an hour. Hello and welcome back to Introduction to Fortran with the Grayscott reaction. So, just I forgot to speak about the aspect, the supposed aspect of Fortran style. Most old Fortran is written in all caps. Don't try it at home. The Roman Empire was writing all caps. I just tell this, you do whatever you do of this. So, the hands-on will start with the link to the GitLab Grayscott Fortran tuto. Okay, it is here. So, please connect your browser to this place. And do I need to resize or is it good at the last end of the class? Almost? One more? Good? Okay. So, this GitLab contains all the code in example. We have the definition of multiple Docker image that I will point you to. In fact, this week we'll use only one of them. So in deployment, so you should be using, maybe I will pass the command about this one. It's 750 megabyte. So if you happen to use Podman, I will display the command to type in the Discord. And I will also pass the link to the GitLab. So to get some usage of the Fortran language, we will be looking at the start example code. Okay, so not yet in the solutions, but here. So we go into examples. And here, the main file you will find are some makefile. We'll start the first compilation with the makefile. On some source directory. And this source directory has 4 parts. Okay, we'll not go into the detail of HDF5 util that is tailored to capitalize on the HDF5 library. Very powerful way to store data. Okay, so it's better if I open it. Okay, so this is too small. So In the back, what size should fit? A bit more. Okay, perfect. So we move to examples, on to source, and here we see that I'm a Max user. Oh. Okay. So we'll start with the main part, which is not very big, the main program. Okay, it should be good this way. Okay, so here we have a main Fortran program. We are referring to some we are using this floating point precision module, which is the smallest module you can consider. In fact, okay, we declare the module, and in turns, it uses an intrinsic module, one given with the language, ISO Fortran env. This is a very standard way to benefit from the common knowledge of all the constants related to your compiler on your system. And we redeclare the real 32 value as PR for precision. Okay, so in the past, I was calling this module precision only, not floating point precision. And Fortran has not quite the idea of reserved words. So precision is a part of an old type, double precision, that is still maintained, but in modern Fortran, we'll declare it as real kind equal real 64. So it's not a problem. You can also have a variable called E for do, which is a very wrong choice, so please avoid it. I renamed it floating point precision to avoid syntactic coloration, meaningless syntactic coloration. Okay, so when using this, every declaration of real constant using this PR will be real 32. So it means that by switching in only this file to real 64 or real 128 or in the future real 16, you can recompile our program in a new resolution. So please use this. Okay, so then we'll be using widely, no only here, the big part of the program, grace code settings. On this initial version, it is not has not a proper design because we mix in the main program a lot of concerns. We call something which is in the grace code settings, the procedure init grace code settings, we init the fields, then we read some data, and we allocate some file. So from a computing engineering point of view, it's not a very good program. And we start to have already OMP parallel. Here we don't know if it will be used by the functions. and we write out the solution. So write out is likely to be defined in this blanket module Grayscale settings. Okay, so let us address this big part. Okay, in Grayscale setting, we are speaking of the parameter you start to know from all you have seen up to now. So we define some default value. Integer is a variable, but as it is initialized, it's a static variable. In Fortran, it's the case by default when you initialize. If you want an automatic variable, you have to initialize after the declaration. We have some module global variable to decide, logical variable to decide whether we'll write the data at the end of the simulation or not. We define how many steps of simulation we take before saving an image of the current state. Okay, old Fortran has a logical unit numbers, so here I take one for input and output. In fact, you have in ISO Fortran M the standard input and standard output if you want to proceed like in C. And here we enter the realm of interesting physical parameter, the time step, the diffusivity of the two species, the feed rate and the kill rate. And here we have two pairs of array, U0, U1, V0, V1, that will be allocatable on two-dimensional. Okay, so we have dynamic array, which means that instead of proceeding like in Jurassic Fortran with fixed value, we could only proceed at max with this fixed value. We will be able to change the value at the start of the program and then allocate the memory dynamically. Okay, so you have seen that a large part of this computation relates to a stencil. So two aspects here. The first aspect is how we initialize some stencil. So the modern Fortran way illustrates perfectly the fact that contrary to the common belief, indices in Fortran don't start at 1. You can define it here from -1 to +1, then -1 to +1 on the second axis. And then we define with this bracket an array constructor, 0, 1, 0, 1, -4, 1. So a 1D array, and we reshape this 1D array as a 3x3 array that will have these indices. Okay, some detail. I specified in the array constructor the type of the value, because if I had not put this real PR, so not the parenthesis after real means real kind equal PR. So you can set the generic precision of your program. So we introduce this here in order that 0, 1, 0 not be understood as integer. Okay. So I am told that there is some question on Discord. Okay. About Okay, I start with the last one on get back. Does the language follow a similar file naming for other Fortran version? Okay, so you will find 4 names as a standard. .f does not mean Jurassic Fortran. It means Fortran with a fixed style. .f90 does not mean you have modern Fortran. It means you have freeform style. So you can write commons, you can write equivalence, you can write, give me some other idea of dirty Fortran. You can write very bad thing in F90. It does not guarantee you use modern Fortran. All of it is interoperable. Okay, so this is .f on .f90, simple. When you have capital F, uppercase F, it means that your program, your source code, will pass through the preprocessor before being compiled. Yes, you can preprocess a Fortran file. It's maybe not completely advisable. Depending on your preprocessor, you will have issue. You can not declare macro with some kind of macro with concatenating argument. Okay. But it's very useful in a lot of cases. And similarly, capital F90 means freeform, but with the preprocessor. Okay. You can see as well .ftn, which means .f. It's not as universally practiced. .for exists as well, but there is no strong binding, strong commitment between this convention and the language itself. As for F03, F08, F18, F23, most compiler will accept it, but with the same meaning, exact same meaning as F19. So the biggest difference will be .f fixed form, .f90 on follow-up free form, and if the F is capital, it is preprocessed. Okay, so Léon asked, or no, replied to Alban about, okay, this usually gets in the way of vectorization. So Alban asked, are given with simple array, but if you design code using structured type, does it become more tricky? So yes, this we will discuss next week. If you want to vectorize with a structured type, you usually need to turn your array of structured type to structured type of array if you want any kind of chance of vectorizing. Okay, so before Alban, Joseph asked about intrinsic. So there is the keyword intrinsic in Fortran 03, right? But in fact, you had intrinsic functions before this. Yes, in F90, you will, as I explained, see a lot of variant of modern Fortran. 90 is not limiting. And the intrinsic keyword allows you to specify that you don't want to use the local version of the name, but the intrinsic one. If not, and you have declared your own sqrt function, it will bypass the one of the library. Okay, and so for Marco, no, there is no. Okay, modern Fortran is a freeform Fortran. On each layer of the norm introduced very much more detailed things, but you cannot guess from start if what is the last version of your code. You have to use the std flag of the G-Fortran compiler if you want to limit your capability to some level of the norm. So yes, use F90 at the end of your files. Okay, back to the code. Okay, so the first things were addressing how to declare a stencil with the proper size, shape, and sorry, I modified it, and type, real. So here we see that we can declare a parameter array. So I guess it started with Fortran 90. And this is really convenient. The other part that we could discuss about is the stencil we told you about is in fact one possible stencil among a two-dimensional space of stencil mimicking a Laplacian. So we don't have to settle with this cross standard Laplacian with -4 in the start and 1 on the center of the exterior. The one of choice for this school is WP for wait pretty. It's nice. And you also have in the literature of simulation, the Patra Kartunen from 66 and the Ono Puri from 88. And here we choose the weight pretty, but this is a parameter you can play with. But before playing, we have to address the computation. So some not so modern Fortran, which is often neglected, is the capability to declare name list, and it allows you to avoid a lot of stupid parsing. So here we see some example of the parameter file in Grayscott settings NML for name list. So in this file, we provide with an ampersand the name of the name list, in this case, Grayscott. And we have this variable name equal value plus some comment. And as usual, always use Unicode in your comment when it can increase the readability. We have the two diffusivity for the two fields. We have the feed rate, the kill rate, the image width, image height, number of steps. So we will not start directly with 32,000 as our first program is really not optimized. And here we provide a logical value to start not writing HDF5 in the first example. So your name list maps this file to internal variable. For some people, it's a bad practice as it couples the exterior of the program to the interior, but it's definitely a very convenient way of parsing, so that you don't have to parse by yourself. In fact, namelist existed since 77, and you should definitely use it. Okay, so some parameter will be looking for HDF5 to this file with this file name. And then the first subroutine will init grade Scott settings. We, as I mentioned, will be using std error on std out from ISO Fortran env to display the things. We start, this inquiry is incorrect, but you will see the correction in solutions. We'll open and read the name list file here. So we read from this file path equal NML. We open the name list, and we read this name list from the file in unit FU. So you can consider the unit as a kind of file handler in C, or file descriptor. So here I exemplify some modern Fortran. In the past, you had to settle on constant value, compiled value at the start of your code for the value of the unit. From Fortran 08, you can ask your program to dynamically determine the not used file handler and returns it to you in some variable that you will use afterwards. So here we read the variable, and if the IOStat is correct, if we have no problem in reading it, so if there is a problem, we report an error, and we write the name list to the standard output, which is the screen. So this means we'll provide a return on the value we have read. We have read or not. So if there was any kind of problem, the file is not here, whatever, the values are already defined before at the end of the module, at the beginning of the module, and we can still run with the default value. So in this case, we proceed in a non-obstructive way of programming. Okay, so now we have the value for the size, and we can properly close the unit from which we have attempted to read or succeeded to read in the best case. And we allocate our 4 fields. We can then set up the HDF file, but we will not enter this, the detail of this aspect. On the first function we can define, we'll compute all the Laplacians for the image. Okay, this was the first choice of the first implementation. So we wrote it in the old classical way with a big nest of classical do loops. Okay, the nice part here is we go up to size along the second dimension of the array. So this is a way to make your program more flexible. On the internal nest of loop over Sj and Si, so please check that the innermost loop in Fortran, we attribute it to the contiguous data. It is right for the innermost loop of the topmost nest, as well as the innermost loop of the second pair. Okay, so this is the less slow way to compute all the Laplacians. So this was the first attempt, not the most successful. There is also some initial condition for the field that are settled here. So you can see the power of expressiveness of the array notation. We declare that the first line is full of 0, on the last line as well as the first column and last column. So this kind of array notation is very expressive, and we do the same for V0. Okay, the first attempt at writing out a solution is with simple write to some output file. We pass the two fields at the end of the simulation or at some point of the simulation, and we write it in an unformatted way, so it can be stored as binary. So we'll see tomorrow that when you have floating point values, it's better to store them in binary because you don't introduce any kind of decimal conversion that in turn may lead to some rounding error. This exemplifies the notion of impure subroutine because it cannot be pure because there is a write. Okay, in this case, we don't have arrays of fields, so it's not elemental, but it's impure. So you can specify if you explicitly says impure, it means you know that there is something that will prevent your function to get pure someday, because of the write in this case. So it's a good practice to use it on a recent compiler to make your code more strongly explicit. Okay, so we have seen all this. Now we might want to get it run. So I will start answering the question before getting into the hard part. Okay. Marco asked about the fragment of code, which is here. Okay. One more. One step bigger. Okay. So, as Manohar says, but there are details to be provided. So we define a constant known at compilation, so-called parameter, with an undeclared length, which means that the length will be fitted from the length of the literal value here. So when we are referred to this variable or constant name, it will contain this, and it is declared this way. The same goes for this set name, which has a different size, but which will be accommodated by this length equal star. Okay, then Joseph asks, would the new unit equal few have to be replaced by a unit equal 10 approach for multi-threaded program. Okay, so this question enters the realm of multi-threaded input-output. I have no example at hand. So for people interested in this, there is a nice chapter in the MPI lecture of Idris. Go on their site. For the standard write, input, output, write and read, I don't think it would be a problem. Okay, we'll try to build a minimum working example. Okay. So I run the Podman container. Okay. Okay, so one more. Oh, good. Okay. So I'm in example in the image. I have the source file here, and I boldly make the compilation. So, okay, there is some remaining issue here. Some argument is not used because we only write the V field and not the U field. So something that is a good practice, you see here the explicit list of flags of the compiler, maybe an exaggerated list, but the first is very much needed, particularly when you start modernizing old code. You set as much warning as possible. Warning all, warning extra, because all is not all. Warning pedantic, if you are really set on this. Warning conversion will be painful. Okay. Fortran is quite strongly typed, but definitely not as strongly typed as the Ada language. It allows promotion of type. Integer can be promoted to real, single precision, double precision. Float can be rounded to integer or truncated. And so when it's not explicit, you don't know. So you want to avoid this kind of lax programming. You want to be more strict on your usage. And warning conversion will tell you about it. Warning shadow has not much use in old Fortran, but in modern Fortran from 08, you can have variable inside the nested block. that will have the same name as a variable outside, but inside the nested block, this new variable will shadow the more global one. So in C, C++, it's extremely common, but in Fortran, use it as well for the few cases that it will save you. As I told you, also the F implicit known constant is a must. Don't try it when you start with some old code because it will burst to your face. But when you write code from start, always use it. This one is specific to G-Fortran. I like it very much. We'll see tomorrow that we have in floating point number, so-called not a number. It's a way to express that some computation could not have a meaningful result. It's not an overflow for which you have infinite as a representation. It's not a number. It's like 0 over 0 or square root of -1. Okay. Already we have two different meanings. In the case of square root of -1, it doesn't mean only not a number, it means not a real number. But among the not a number, there are two kinds. There is the quiet not a number. Some computation doesn't give a meaningful result. We put none in the variable, and this none will slowly contaminate all computation using this variable. And in the end, maybe you still have something meaningful, but whatever is meaningless will be marked as none. Okay. Signaling none, S-none, on the other hand, mean when I find one, when I use one, when I read one, I stop the program. So this way of using initialize by default all real variable to signaling none forces you to have some value put in the variable before you can use it. See, this is a very good way to avoid forgotten initialization without relying to things such as Valgrind that cost a lot of speed down. fcheck equal all will slow your program, so we should get rid of it. Fcheck equal all will test that we are writing inside the size of the array. So we will not be working on some unknown memory. Okay. So this makefile was really overstating a lot of things, but we compiled and linked, including the link with HDF5. And so now we want to run this code. So as we have seen, it has read something. It did not tell you that the file does not exist. And the good news is the NML file contains the same meaningful value. Contrary to what is in the source code with 32,000, here we are more sensible, and we only took 300 steps. Given that the file is not optimized, it's a must. Okay. Yes, okay. Thanks, Vincent, for the link to archive link. As I said, maybe this one is the French one. Don't hesitate to look in the site for the English one. Okay, so some work is at play. Maybe we should check the CPU usage. I arrived too late, hopefully. Okay, so it finished. No display of the time consumed. Come on, I should have used time, but not quite efficient, not quite parallel. Okay, so we should modify this makefile. So here it is. We'll remove this fcheck equal all. Okay, so maybe to have a more sciencey way to approach the problem, we will time it. So I have not recompiled yet. Sorry for the delay. And here we can see how much time is taken. So only one of the CPU is used, as expected. Up to now, it's a sequential program. Yes, yes, this, I should have some pump. Okay, so. Okay, so it stopped the. Okay. So 1 minute 21, 80 seconds for 320 steps. So it's not very efficient. So let's recompile. We start with the. We will recreate all the compilation. And now, when we time it, we expect some slight improvement, but nothing major. We should boil water with this. So you see the process jumping from core to core so that multiple core get some exertion. And the one is not fusing over the other. Okay, so finished. Okay, so removing the systematic check of boundary among the other turns by having the time. We went from 80 seconds to 46. So never forget to activate optimization. Speaking of which, I see that there is no optimization in my flags. Would you agree? Okay. Let me check the compilation flags. Who could tolerate this? So we'll check with -03 on minus march equal native minus march equal mtune equal native. Okay. Okay. So we recompile everything with these options. And we expect dramatic factor 20 improvement. Comme ça. Okay, so we see here we can finally consider to compute on 100 times more data without spending 1 day. Okay, so would I be able to get any kind of vectorization? Anybody interested? Okay, vectorization. So, okay, we'll start with limiting to MAVX2. Okay, there is no meaningful FOpenMP by now. Okay. So, okay, when you optimize, you start by de-pessimizing, by getting the check bounds off. And afterwards, you add the things that make it faster. So F3 SIMD, F3 vectorize, as well as some detail. Okay, these two things will not improve the vectorization, but the compiler will tell us what it is doing. Okay, we might want to have some f-unroll loops. Why is it not here? Okay, maybe it's implied in the optimization, but let's explicit it. Okay. Same operation, make clobber and make. The code is small, the compilation is quick, but in fact, okay. So I forgot a very important thing. I want to add to the flag and not overwrite. because if there is no optimization, the vectorization option will not do it. Okay, and here it's more talkative. The compiler tells you a lot about the job it is doing. Tells you that in such and such line, it is optimizing basic plug being vectorized using 16-bit vector, 2-bit vector, 32-bit vector. Okay, so before you start using the specialist tool that we...
I just wanted to ask if it...
Yes, I copy it in the...
Okay, thanks. That's all.
Okay. Okay, so a lot of questions appeared. Hopefully, Joel is answering about the fine detail of vectorization. Okay, so okay, I start answering to Carolina. How do we conclude from n steps that the code is not quite efficient or parallel? Okay. Prior evidence. So I should have explicited it. So Giordano asked us which software we are looking at here. Okay, it's only on one thread, so with a 16 hyperthread, it was not very much seen, but it was the topmost line, base grayscale from something that was using 6.2% of CPU, which is exactly one core in this 16 core. Okay. About the question of SI, isn't it less efficient to use 2D or 3D array rather than 1D in Fortran? No. Okay, so this is the very good part of Fortran. Hopefully, C++26 is about to be as good after 57 years. 70 years, sorry. I tried to run make again after removing the fcheck and got make. Okay, so Joseph, before making some code after modifying the make file, making it again, you need to recompile because you need to, clean away all the objects on executable that have been provided by the previous run because the make file considers that the source has not been changed, and so make doesn't make anything. I hope it answered the question. Okay, got it. Friendly way. Okay, so I leave it to Joël merci Joël to answer Sai. So, yes, here we were with potential vectorization, and we will time once again. Okay, so not much has been won by this early attempt at vectorizing. So maybe it was already vectorizing with the O3. Maybe it could not find enough things to vectorize in spite of its very lengthy explanation of what it did. Okay. So, up to now, we have not expressed any kind of parallelization. And if we want to benefit from the power we are discussing from the start of this school, we need to go into more detail. On this first version of the code that I provided for you to play with, we will move to a more engineered version. Okay, yes, there is something I can do better, because on this machine I don't have AVX2, I have AVX 512. And then there is not one AVX 512. There are tons of variants depending on your specific hardware. So you don't need, you cannot suffice to say, okay, M-AVX 512F, because it's not M-AVX 512 only. Why not? Okay, so make clobber, make, doesn't move. In fact, let me find it. Okay. Depending on your AVX 512 processor, you will need some such set of flags. So I pass it for your pleasure in the Discord, but it depends on your hardware, and I cannot guarantee it is the right set for you. Yes?
If you push March equals native, it will push all the flags that you need. So you don't need to, like if you push March native, you don't need to push AVX, whatever. Like you don't, if you push dash M March equals native, you don't need to push dash M AVX 112F, etc., etc. I'm sure.
Okay, okay. So we already benefited from all of it. So I have practiced over older generation of compiler, and from time to time.
It may be the case if the compiler is outdated, then it may not recognize.
But you're right. Here we have the pleasure to operate with Fortran 15, which is definitely recent. Thank you. So, okay, indeed, it doesn't change. So this is good as a endpoint for this first part of the hands-on. We have seen a very naive implementation. We have not seen parallelization. We have just seen that before getting into more details with a program, you should always start knowing your compiler, knowing your hardware to get the most benefit out of it. It's some knowledge that will expand with time because when you started with GCC 2.95 and you arrive to GCC 15, things change. We'll see this afternoon the more interesting part about parallelization, and I leave it to Pierre.
Okay, if you are curious for the compiler, it's since G++ 11 that you have the automatic MRChigal native with all the flags that you want. But now it's time to go for lunch. So we'll have a little break and we'll start again at 1:30. So we have the presentation of Luxembourg and we'll have also the visit of the LAPP museum. So for those who are in LAPP, of course. That being said, thanks everyone for following this session this morning. Thanks all the satellite side. Thanks everyone for all the questions, all the answers. See you in 1 hour and a half.
are live. The floor is yours, guys.
Thank you.
Okay, so thank you for being here again for the third day of the Grace Scott School. We're very happy to welcome Georgios Katsanas from the University of Luxembourg, one of our dear partners for the Grace Scott School. So you can ask any questions for Georgios on Discord. Don't hesitate. He'll do the presentation, then answer some questions. And even after the presentation, you can still contact him through the dedicated channel on Discord. So, Georgios, the floor is yours.
Yes, thank you, Mary. So I'm Georgios Kafanas. I work at the HPC facility at the University of Luxembourg. We are part of Supercomputing Luxembourg, which is the National Competence Center for HPC in Luxembourg. And we have two clusters in our centers, two clusters. So there is the National Tier 1 facility. It's called Meluxina. It provides more business-oriented supercomputer resources. So in our national facility, we have a CPU partition of about, I think it's 1,000 nodes, about 2,000 cores. They are typical ROM Zen 2 architecture, ROM. There is also a GPU partition with 8100s, about 800 GPUs. And they have a specialized partition also with FPGA, about 20 nodes, which is available for special applications to the partners who request them. And there is also an integrated cloud module that targets more, let's say, business applications. And soon they will have, they're also developing Meluxina AI and Meluxina Q, which are correspondingly the AI factory and the quantum supercomputer that will be hosted at the Luxembourg Tier 1 center. Now I work at the Tier 2 center, so this is hosted at the University of Luxembourg. In terms of hardware resources, we have a couple of conventional HPC clusters. We also participate on Grid 1000, and we provide some. We also host some specialized hardware for some applications. And we support mostly training activities and research. So we have a couple of HPC masters focusing on so a couple of masters focusing on HPC. So we have a local master, and we also collaborate with the EU Master for HPC, which is a pan-European master where students visit multiple universities during their studies. We also provide training to users, and we manage access to Tier 1 facilities for university researchers, and in some cases for student projects as well. Now I will talk mostly about for the cluster in the university, since I know more about them. Our clusters are typical clusters for a Tier 2 facility. So we have usually mixed type clusters, CPU nodes and also some nodes accelerated with GPUs. We use a Lastres file system for Scratch, and we have a GBFS file system to provide storage for home directories and project directories. And also we have a university-wide file system, one FS file system that is used for long-term storage, and it's accessible through slow network connection across every node in our cluster, including access node and compute nodes. And of course, we use SLARM for scheduling and InfiniBand for the fast network. Now, I won't bore you about the type of nodes that we have. So in terms of our clusters, we have ION, which is actually a CPU-only cluster. Same architecture as the Tier 1 cluster, but slightly smaller, and is used mainly to run research software like CFD and solid mechanics simulations. We have some of developers of Phoenix, FAIR software in our university. And we also support molecular and quantum dynamic simulation. We also have a couple of quantum Monte Carlo software developed in our university, like QMECA. We also have a secondary cluster called Iris, which is more it hosts more variable kind of hardware than IO. So in Iris we have 25 GPU nodes. 24 of them are V100s, and we have also one H100 node. And we also maintain 4 large memory nodes for some specialized workflows. And this cluster is used mostly for molecular dynamics and for some deep neural network training applications. So anything related with AI usually runs in the Iris cluster. In the Iris cluster, we also have some older CPU nodes, which we use to provide interactive sessions for our users. So debugging, Jupyter and our notebooks, data visualization, and of course, almost every training runs in our Iris cluster. So yes, the Iris cluster is more, let's say, customizable than our Ion cluster, and we are in the process of moving to an open source stack based on Werewolf and OpenHPC. And of course, in the Iris cluster, we also manage the hardware, and we also have to take care of various incidents, like for instance, in this case, we had a failure in the power supply. In our university, we also contribute to a couple of projects. Even though we're not formally members of these projects, we still have some collaboration agreements. So we contribute to Grid 5000. That's quite popular in France. But it provides access to hardware to institutions across France, Belgium, and Luxembourg. There are various kinds of hardware and software systems available, and it tends mostly to support open science and reproducible research. So researchers can run their basically their workloads in Grid 5 in some machine in Grid 5000, and everybody with access to Grid 5000 can later reproduce this workload. It's in the process of Grid 5000 is in the process of merging into slices, which is going to extend in other areas of computing like edge and quantum computing. Now, in terms of our contribution to Grid 5000, we provide 48 standard CPU nodes and 8 nodes with accelerators. So we have 7 accelerators with MI 210s and 1 accelerator with MI 300X. We also have a special node. It's a IPU, some special hardware developed by GraphCore. So this was basically an effort to implement some basically hardware that supports message passing on a chip. So basically it contains a lot of small cores with a lot of memory in every core, and it allows users to basically write software with message passing interface within the using a single machine and basically exploit the computing power of a large number of cores. So basically our version contains a total of 16 ball-code IPUs. A single IPU has about almost 1,500 cores, and every core supports 6 threads, and basically every thread is addressable from every other node in the cluster with very low latency. And finally, in terms of trainings, activities, and user support, as I said, we support 2 large master programs in HPC. So we have our local master program, which is 2 years in Luxembourg, and we also participate in a master for HPC, where users can they have to attend a couple of universities in Europe, and you can see our partners in the left-hand side. And of course, we develop trainings for the National Supercomputing Center, both in Meluxina and in our infrastructure. And you can find our courses on the internet. And finally, we provide some localized trainings for HPC for our users. So we have trainings at the university both for HPC and machine learning. And yes, in terms of access to our systems in the university, every student is entitled to an account. It's free at the point of use. We have some extra controls in place to ensure better access to some labs that host their resources in our cluster. So participants of the lab get better access to their resources, but everyone in the university can use them. In terms of the national HPC facility, we support all the researchers that want to transfer their workloads to our national facility or any other Euro HPC system. And we manage access to Meluxina projects, to Meluxina for projects within our university. So researchers in our university who want to access Meluxina, they just have to request access and we mediate to Meluxina for them. So yes, thank you very much. That was our side. I'm happy to answer any questions.
Okay, thank you, Georges. I hope, yeah, you can hear me. I thank you very much for this presentation. I'm sure that you're gonna have many contacts, many questions for all the activities that you were talking about and the presentation of your cluster. So if you have any question on Discord right now, please enjoy the moment and you can ask Georgios. If not, you can always write for him on the dedicated channel Luxembourg site on our Discord. So I see someone is writing, so maybe we'll wait just a little seconds. Okay, now you have congratulations. Yeah, and I agree. Very interesting.
Yeah, I'll be happy to answer any question if you post in our site. Thank you very much.
Yes, thank you, Georgios, and thank you for being our partner. It's great to work with you.
It's our pleasure.
I hope we can do many things together. So for everyone, we'll meet at 2 for the afternoon courses, and so you have time to grab a coffee as always. Thank you, Georgios. See you soon.
Thank you.
presentation of parallelism and optimization in modern Fortran. I will present you in this last part on CPU in Fortran. The part after introducing optimization by the compiler, the flags, the general setup, the build process, we will enter for good the way on multiple way in Fortran to parallelize your code. So here we go. So, to remind everybody about the situation, we are running the Podman container that we introduced this morning. And after getting into a first version of the code, we will now turn to the ones that are presented inside the subdirectory example solution. So we will proceed with compiling the various code that we'll use today. The first thing is here to use CMake, and as expected, we start from a fresh build directory. We move into it. We invoke CMake for the file that is, in our case, two places above. It goes nicely. So let me show you this in the Discord. And as CMake succeeded, we can now execute the makefile. As you can expect, after the option, the flags we have seen this morning, it will be a tad verbose. So here we go. But in fact, it is not that verbose, thanks to the terse aspect of CMake. And we have produced a bunch of solutions. Okay, so we will start by comparing the code. So this morning we had some first version. And here you can see, let me put it slightly bigger. Okay. So on your left, the module grace code setting of this morning on your right, the one we'll use. So the default values are slightly different, but as we know, we override them by what we have from the external file. Everything stays common. We'll use some dirty trick for input-output here, in case we should decide to use them. In order to be as fast as possible, instead of writing it on the disk, we'll use the memory disk on the benefit of a large unmerited speed up. Okay, so this morning we had a function computing the Laplacian over the full field, and we decided to go along the way of the other colleague. And so you see that here we replaced it with a subroutine evolve, which runs for all the steps over all the points of the field and computes the Laplacian with this simple formula. This is where the expressiveness of Fortran takes its best. We take the product of the stencil, which is a 3x3 matrix. We isolate some submatrix 3x3 around the point of interest in the U0 field. And multiplying and summing the two gives you the result in one line. Let the compiler take the best out of this expression. Okay, so we do it for U1 and we do it for V1 in a very similar way. Once every 2000 iteration, we'll write the number of iterations to follow up and not be alone in front of the screen. And in this case, we chose a very inefficient way to proceed. So now, contrary to the previous version, we do every computation inside the module grace code setting, and when we look to the main program that we can find here, we see that it is restricted to the really most elementary way. So what we use as a public part, this much, even more. When we use this, you can see two things. We now specify that we only use these three subroutines, evolve, init field, init grace code setting. Everything else is inside the module, private part, or as good as private. And we will display, okay, so system clock provide us some count and with the precision of the smallest time increment generally available on the system. So on some system, it was microsecond. In the case at hand, it will be most likely milliseconds. So don't worry, we are wrong by a factor of 1000, but you will quickly notice it. Okay, so this is a very elementary program. This external in front of implicit known comes from the Fortran 2018 norm, and tells you that you have to define every interface to some subroutine. not only you have to define every identifier variable, but modern Fortran is asking for more and more constraints. Okay, so here it is for the code. Sorry. And we know that we could compile it. And it is called pre-OpenMP. So it should be almost as good as before. Okay, so time will not be necessary, but it will help us calibrate this factor of 1000 that we expect to be wrong. Okay, so 17 seconds, almost 18, displayed as 17,000 microseconds, so you should read millisecond. And okay, we know that it's 8 times worse than what we had this morning. So most likely due to not optimal choice of compiler flags. And what we want to do from now is to parallelize this, because there is a lot of parallelism expressed here. So we will compare this pre-OpenMP to the first and easiest way to parallelize something, which is OpenMP. So do you want some time to try it by yourself? Starting from pre-OpenMP F90, produce the code. So as no majority is emerging, I will walk you through what is changing from one to the other. Okay. Okay. Discord. Yes, absolutely. It's limited to how much RAM our system has. I have not tried to use a swap. I have not checked that it uses a swap. So in our case, when we have the full simulation running, we'll use 8 GB of H5 file. So in my case, it will fit, but if anybody try it with less than 8 GB of memory, or if you play with a larger thing, it should be an interesting result. Okay, so not much to say here. Okay. So where things start to differ is in our new evolve routine. We have kept things very similar beside this strange notation. So as I forgot to tell you, the exclamation mark is the modern Fortran marker for comments. So we have just added comments. How could this produce anything? So we have what is called a sentinel. When you have the dollar with the comment, the compiler, when used with the proper OpenMP flag, will make use of the special capability of OpenMP to multi-thread your code. And beside this conditional compilation, this will only compile when you have the proper FOpenMP option. These are conditional compilation with the Sentinel OpenMP that lead to a clause. We declare that inside the big time loop over n-step iteration, so this external loop here is in fact a sequential one, non-parallel one, but inside it we have a parallel region where the following variable n steps u0, v0, u1, v1, iter ig are shared between the various threads of the parallel region. And in each thread, you will have a private copy of the Laplacian variable. Okay. And then inside this parallel region, we will share the following loop, in this case, the outermost loop, among the various threads. So we'll share the work of the very big loop behind them, among the various threads. And now we introduce something else, OpenMP SAMD aligned. So we tell the compiler not only to have multi-thread on the top loop, but to have vectorization in the bottom loop. So once more, the pincer movement to exploit to the most the power of our processor. Inside the loop, nothing has changed. And we end the loop. So modern compiler tend in Fortran not to need this last part because they recognize the end of the do loop that started. So it's mostly for you to see the symmetry. Okay. Afterwards, we decide that all threads will not be producing output, so as not to bother you too much. And so we have some conditional compilation. If we are on the so-called master thread, the name has changed. Master thread was not politically correct, so now we call it somewhere else, something else. So this part of the code will in fact run only on one of the threads. And then we have another loop to copy this, which I should say is in fact really a loss of time. Okay, so what do we have with this? So we want to use the one that has been compiled as OpenMP. Much better. So we were at 17 seconds, and now we are at only 3.3. For a total user time of 51 seconds. So the threads have been using a lot of time, much more than the sequential, 3 times as much as the sequential thing. Okay, so it will be difficult to see so few thing, okay, on this. I run it again, and you see that all the cores get saturated. But among these 16 cores, so let me just make it a bit smaller that we see all of them. Maybe even yes, from 0 to 15. Okay, so you had this short burst over there where we have used the thread on the hyperthread. And it's likely that this has not been helping. We have lost a lot of time waiting. This is why the complete user time here is more than the initial thing. Okay, can we specify this? So you have environment variable in OMP that allow you to restrict the number of threads or artificially increase it beyond the number of core. And we limit it to the number of physical core this way. Okay, so I should have run it with time, but the wall clock time is good. So in this case, we are also at 3.something seconds. And here you see that the CPU have been used at 800% because we have 8 core. And nothing has been lost in the system. So does it change when we don't use? Okay, so with 4 core, we expect to see more wall clock time, and in fact, it's not a factor 2. We are losing when using the 8 thread, something is not efficient. Okay, so we should play with yet another version. Because as we have seen, the second part of the code here is really useless. We put back in U0 the value that have been computed at the given step. So it's easy to do better than that. So here we will do only half the number of steps, but we will include in the first part, we'll do 2 steps at once, one moving from U0 to U1, and then another one from U1 to U0. And instead of doing stupid work with copy, we will do interesting work with computation. Okay. So for thread used 6 seconds, and we are only marginally better here. What do we have with 8 threads? Okay, 3 and so seconds. So with so few time, in fact, you see, okay, a short burst. It's hard to collect. Okay, but 3 seconds for 320 iteration will move to 300. We'll move to 300 seconds with the full movie. 300 seconds will be 5 minutes. So now we can start using, we could start using the program in real mode. Okay, maybe there is something to gain with vectorization here. So we keep the same code, but this time compiled with different options. So the first one with the stupid copy of data, but with vectorization, does it improve? Not much. And so it was certainly thanks to the Fortran 15 already improved. Okay, so the new version is only 10% better. So from this, what is the next step? Okay, pre-OpenMP, OpenMP bis, OpenMP vectorize, OpenMP bis vectorize. So I told you this morning about the benefit that we should exploit in modern Fortran. That are called standard parallelism, STD-par, and that the NV Fortran compiler will make you able to use at length. Okay, so here we change some more things. We still, okay, so I will compare from between OpenMP bis, the one where we do not have a stupid work, so I'm comparing the last source code we add to some new expression where we don't have an OpenMP statement. We don't explicitly ask the compiler that so this and this variable must be shared between the thread, but this and this variable must have a private copy in each thread. And we replace this with do concurrent. Instead of 2 layers of loops that we have here and here, 2 layers in the nest, with a single do concurrent that we don't even bother to organize with J first and A second. The compiler is a big boy, he will do it. We keep the same expression for Laplacian of U. So we add in comment the old way to express it if you want. This one with single elementary do loop, as you do not need to parallelize them. It's too low level. And so we do the same thing, but we will rely on the compiler to detect the parallelism of the do concurrent. And in the same way, we have a second one where the do concurrent does the job back from U1 to U0. So it is compiled in this, and it has been compiled by telling the compiler. So nowadays, the G-Fortran compiler can exploit this as well. Okay, so something has gone wrong because what we can see here, we do not seem to have a big burst of so only one thread is activated. So it's likely that I missed some option there because it's running not in parallel. So the do concurrent has not been exploited. Okay. Should we look at the CMake list that generated this? STD par multicore. STD par CPU and proc. Okay. So we have not discussed yet this option that some year before existed only with NVIDIA Fortran, which is F3 parallelized loops that allows the G-Fortran in principle to exploit so many threads. In this case, we have set the number of threads to the number of cores, including the 16, including the hyper-thread core, which are not completely useful in this case. Okay, so STD par GPU, STD par multicore, native. Okay. So it's not quite convincing on the G-Fortran part, but we'll see next week that NV Fortran is up to the task. As we have seen what kind of optimization we can have from the compiler side, and from the algorithm side, you may agree on the fact that it's not quite elegant to have this duplication of code, even if you reverse it. So I suggest that we use a functionality of modern Fortran. In this case, which are in fact pointers. Okay, so we look at the code, and the first thing that changes is here we have pointer in this new code where we add allocatable here. Okay, what will it change? Okay, we include some new routines, a routine to swap the field that defines a temporary pointer and swap the pointer to U0. Then U0 will point to U1, and U1 will point to TMP, which is the old place where U0 was. So in this way, we can swap full array without copy. And the same goes for V0 and V1. As these are pointers and not allocatable, we have to deallocate them by the end of the code. Okay? So we can be back to a normal number of steps. And here, the OMP parallel version stays the same inside. And instead of duplicating the code in some stupid way, we call the swap field that will just swap two pointers. Okay, so does it work? I swap the pointer version with the standard and recompile it. Okay, sorry, I'm going to build and recompile it. No. Okay, so it has been regenerated. And now we execute with 8 threads the new OpenMP bis with pointers, and the time is as good as the OpenMP bis we had before. So we have not lost in performance, and we have won on the elegant side of the code. So pointers, which are not a favorite part of Fortran, which is an unknown part of Fortran, can be beneficial. Okay. Now, we compute fast, but do we compute with enough precision? Because in the end, we'll see very nice movie as you have seen yesterday, and you will continue to see. But the result may have more accuracy than just beautiful plots. Beautiful plots, we cannot see if it's good to the 1 part in 100, but maybe for some computation, we need 1 part in 10,000, 1 part in 1,000,000. So we have, let's say, some issues like this, some issues with the numerical part of the code. Okay, so this morning, I have shown you the various stencils that we could use. In practice, what did it provide last year? So these are 4 excerpts of the different stencils that I naively stopped at the same point in the process. And the one we use is really impressive as far as the results are concerned. But the Oonopuri was not delivering the same simulation. What was wrong? For Patra-Karttunen and central difference, it was even worse. So it was much time to have a unit test in Fortran. Are we sure that our stencils are real Laplacians, or as close as a Laplacian as you can get? Particularly when you read all the hype in the scientific paper about the famed Patra-Karttunen systematically derived by imposing condition of rotational invariance, and the Oonopuri optimally isotropic form of discretization. The movie doesn't tell this story. So what went wrong? So the first thing were simple typo. Here, I had let 0 instead of -20. Of course, with this, so Patra-Karttunen would simply explode and you would not see anything. Okay. In the second case, Oonopuri, I got the number in the stencil correct, but the dividing factor was 3 times too big, which explained that Oonopuri would in fact not develop as fast. It's as if you were cutting the diffusivity by a factor of 3. A factor of 3 related to what? Because in fact, Wade Pretty, which is really pretty, is also a bit obese. He has a wrong normalization, but we have not yet seen it. Okay, so when I realized this, it was shocking, and I needed to determine the test. So if you move to Wikipedia, you will see that all these discrete Laplacians can be parameterized by one value between 0 and 1, which is the gamma. With gamma, you have the pure central difference CD stencil, this one, very popular with people doing MPI, because you avoid communication along the diagonal. So instead of getting 8 communication for only one corner in this case, you only communicate with the large side of your domain. The diagonal difference stencil, which we had not even mentioned up to now, is in fact some rotated version of the stencil, of the central difference stencil, but with a factor 1/2. So there is some way to normalize things properly. And all the stencils we have been playing with are normalized version of this two-dimensional space combining central difference and diagonal difference. So the one we like, weight pretty, is the equivalent with gamma is 2/3. The Patra-Cartoonen is with gamma 1/3. And the Ono-Puri with gamma 1/2. Okay, so at least we can generate various things that should give the same result. So we have not spoken much about it, but how to practically have some discrete Laplacian. How, from a discrete set of points, can we mimic the second derivative? So, okay. No, don't worry. Yes. Okay, so we have a stencil with this 9 value that we can index minus, minus, minus 0, minus, plus. And when we compute it, we have this sum of this coefficient, Cij, times the discrete value of this function on a grid. And in a continuous case, it means f evaluated at some central position plus -1, 0, or 1 times one step of h, the discretization step. The second coefficient goes the same. So when you expand, oh yes, it's really small, but it's not long. When you expand your result using Taylor, you get this value for the 9 discrete value of the function, the central value plus IH times the derivative along x, JH the derivative along y, and so on for the second order, including the cross terms. So what we are computing is the central value times the sum of the Cij, all the value in the stencil, the derivative of x times the sum of the value of the coefficient times the index I. For the derivative along y, it's the same but with j, and so on. And what we expect, if we want to have this discrete sum mimicking a Laplacian, it requires the following condition. The sum of the 0th order term should be 0, and the sum of the first order term should be 0 as well. The cross term should be 0, and the quadratic term, they should be equal and equal to some value. And this is where the normalization is at play. So when we choose a given stencil to mimic a Laplacian, it has to respect this constraint. Okay? Up to now, we have 5 linear equations on one affine one, but a total of 9 unknown. So we are left with 3 degrees of freedom, but we already know 2 of them, stencil with the central difference and stencil with the diagonal difference. Is there a third one? No, because we can go further. We can expand to the third order. Okay, so not much help from here, but when we pursue the development to the third order, we get 4 more equations. Okay, but then we have -1 degree of freedom. We are over constrained. In fact, these linear equations are not all independent. The equation 2 on 9 as well as the 3 on 10 lead to the same equation in practice. And so we have only 1 degree of freedom, which is the case with the parameterization with gamma. Okay. So, back to some Fortran. And we want to check the constraint. And in fact, it will be a kind of dot product of some constant value with our stencil. So for each of the constraints, we define a 3x3 matrix that will, when smashed against the stencil, lead to the proper value. The first value, the sum of constraint 0, it's all 1. It's a constraint 0 over here is a uniform matrix of 1. So sum of constraint 0 times the stencil is the sum of the element of the stencil. And as you have seen repeatedly, all the elements of the stencil always should sum to 0. Okay, so this one is easy, but the following one are expressed in a very similar way. And so you can, from here, build a program that will quickly tell you you can continue using this stencil or not. Okay, so what are the expected results? So here we construct some array from this value. So it's a good practice to, when you define a composite type, to build it, to construct it all at once. In this case, the compiler can tell you if you are forgetting something. On the expression of these constraints that you see in the mathematical form here should be equal to 0 for the constraint 0, 0 for the 1, 1, 0 for the 1, 2. Okay, so the first index here is the order of the constraint, which is the order of the derivative that are suppressed or not. So we go up to the third order. And only the part 2s will lead to a non-zero result, which is the normalization. And we expect that with this given set of data, the normalization should be 4. And afterward, we can check in a very compact way, very expressive way, computing on a given stencil, for instance, the one of central difference, all the constraints in one go. This function is returning, as you see here, the return value is in fact an array. The return value of the function is a one-dimensional array. Allocatable, which allows, since Fortran 08, auto-allocation. So Sébastien will tell you to be cautious, because in modern Fortran, a lot of temporary variables can get allocated on the spur of the moment. You believe that you have only computing nice things, don't know dynamic allocation, but the compiler has done it for you. It has a nice side, so you can define the memory required for the return value instantly, but of course there is a price to pay. You have to check that you are not allocating too small things. In this case, we are in a unit test and that will get popped on pop, pushed on pop in a fraction of a second with only 9 elements. It's not a problem. In other programs, be cautious. Okay, so here I check the one for central difference, and we have some array, the result of compute stencil, being equal to the array of the constraint, and the result of array equal array is an array of logical. And the same goes for all the other stencils. And you get a result like this. So for the central difference stencil, all the constraints are true, so it's a good stencil. For the diagonal difference stencil, DD, also the same. Ono Puri is correct. And then the Patra Kartunen is wrong in 2 places. Okay, so the test has been useful. We know what kind of constraints are violated, and we can check in the literature and in the program if we mistyped something. Okay, so what about our favorite stencil, WP? It is false in 1 place, and this place is the normalization. Okay, so when you look at the discrepancy on the constraint, because as you will learn tomorrow, but maybe you already know, we are doing something very naughty. We are comparing floats. You should not be comparing floats. Most of the time, it works. But in the case of Patra Kartunen, when you, instead of displaying the equality, you display the numerical difference, and you express it as the number of machine epsilon of your system. So we'll see that it is the quantum of accuracy at a given precision. You see that, okay. This is maybe not the machine epsilon, but simply some very small value, but we see that the discrepancy is very small. Okay, machine epsilon should not be the right things to check when you are comparing with 0. Okay, so for Patra Kartunen, we have some rounding error, very likely, because the Patra Kartunen stencil is built from things that don't provide an exact result. Okay, so you divide by 6 at some point, and even in binary, dividing by 3 doesn't work. Dividing by 5 doesn't work. Well, okay. So much for the Patra Kartunen. And for the weight pretty, we have tens of million, almost hundreds of million, 100 of million of machine epsilon. So, of course, the normalization is wrong by a factor of a lot. So, what is enough to solve the problem is to divide the weight pretty by a factor of 3. So not only the Ono Puri was 2 divided, under normalized, and the weight pretty was over normalized. So when you do this, okay, what was wrong before the normalization gets true, so it is solved. But as we are dividing by 3, we introduce this, and this errors in the computation, it's not so much of a problem. We know it's a rounding error, minimal rounding error, so we solved it. So for the benefit of comparison, we keep all the stencil in accordance with the WP, but if you want to do some comparison, multiply all your diffusivity by 3 if you use another one. Okay, and as for the Patra Kartunen, if we allow to lose for the normalization, instead of dividing by 6, we divide by 2, then all the constraints except the normalization one gets true. So this part can be it can be interesting to look at what kind of differences this will introduce. One more point before leaving this aspect. So why all elements of a stencil should sum to 0. So if it doesn't sum to 0, it means that the evaluation of your stencil will, instead of reporting the Laplacian of the function, will report the value of the function multiplied by the sum, which is not 0, plus some other composite of all the other derivatives. Okay, so this is for Joseph. For Lucas, it's not clear for me in this case, the exact equality assertion between float causes issues or not. Okay, so the right way to address the issues of float that I've told you here is to start with the unnormalized but integer version of all of the stencil. Then you crush them to the various constraints, which are also integer matrices, and the result will be an exact computation of integers. As you have changed your integer stencil by only a multiplicative factor, everything that should get to 0 gets to 0, but gets evaluated without rounding error. So you can check 8 out of the 9 constraints immediately, and exactly. Afterwards, you only have to introduce the normalization coefficient, which has been modified by the artificial scaling of your integer stencil. On so doing, you will not lose time. You regenerate the stencil, the real stencil that you want, as the integer stencil divided by the integer normalization, and everything has been equal. So in order to check the last constraint, the constraint of normalization, you proceed with your integer bloated stencil. It gives you a too big result, but you know that it must be 4 times the normalization factor of this integer matrix. And this is integer times integer, no rounding error. So this would be the way to go to get rid of these rounding errors. Okay. Next question. Lucas, is it clearer this way? Okay, so you can think of it as a sanity check. Yes, absolutely. This is a unit test that once more is a sanity check. And you see one of the difficulties with a unit test, sometimes they are so obvious that why should I do it? It's obvious. It will be good. And even for simple thing like this, it is not. Okay, so what the stencil is discretizing. Okay. Nobody wants to have a dirty comment and tell me that I'm lazy and why did I stop to third order? You are too nice. Huh? Okay, so what I did not tell you here is when we expand to fourth order, then we have no more equation to avoid some value leaking. We will have a fourth order derivative in the computation. We will have so-called bi-Laplacian, the Laplacian of the function will be computed in your discretization. So this discretization is introducing terms that in turn are proportional to the fourth power of the step, space step. And this would be a part to study, but you will not see on the movie. It will be really small. This is something interesting if you want to go to 5x5 stencil. This is one of the motivations of having larger stencils. You will have more equations, you can suppress fourth order, fifth order. If odd orders, they have a good luck, they have a nice chance to suppress as a consequence of the first order being suppressed. But, okay, so depending on the level of accuracy that you want, because we want to compute things fast, but we don't want to compute wrong things fast, you can move to larger stencils. Okay. So much for the stencils, or not? Okay, so I'm telling you something in advance for tomorrow. We will be summing values, and if we are on some nearly constant part of the field, we expect the Laplacian to be nearly zero. So we are organizing the massive suppression of positive value with negative value. So we want that in the end, most, if not all the bits of the representation cancel. So we are losing all the information in the result. This is what we call a catastrophic cancellation. Yeah. On this catastrophic cancellation, maybe we are losing the interesting part of the computation. So when you have some that you want to evaluate to the maximum of precision, we will see tomorrow about compensated sums. You can go beyond the precision that you are working with in order to get the most out of your data. And in the case of positive number, you will use what we see tomorrow, the CAN summation, but you have Neumeyer summation, and K-Neumeyer, which is a combination for positive and negative alternating values. And you can also see this computation as a kind of dot product, because we have a 9-dimensional vector smashed against another 9-dimensional. So all these methods take more time than the naive sum. So this is also a good reason to improve the efficiency of the computation before extending it to more stable and robust value. Okay? So is it finished with accuracy? No. No, because we have spoken of accuracy in space. But we are also computing some equation evolving with time. Okay. So here I am. Okay, so what we have done up to now is compute the next value as this term, the next value of u, for instance, as the old value of u plus this term times the time step. Do you know what is the name of this algorithm? When you try to solve a first-order differential equation in time, usually, with one step that is simply adding the local derivatives times the step. Yes. And when you exit your first order of ordinary differential equation numerical method, one tells you, okay, only for playing. You should not use the Euler method for serious computation. What other method could we use? Yes, RK. RK, it's the motor of many numerical methods. Runge-Kutta, they largely contributed to the improvement of artillery tables, maybe without their knowing, for the World War I. So, of course, we have implemented the Runge-Kutta. And we also implemented another, so when we speak of the Runge-Kutta, it's the fourth order Runge-Kutta with fixed step. But we also implemented the cache-cap method, which is a higher order Runge-Kutta that in the same computation provide you with a fifth order evaluation plus a fourth order one. And from comparing the two results, you can see if the step provides you too much accuracy for what you expect or not. If you have too much accuracy, you can take a larger step and then you will get less things to compute. So I did not introduce the Dormant Prince 8th order Runge-Kutta, but if you have the memory and the time, it can be nice to try it. But let us check what it looks like. Okay. Okay, so we clearly see some problems soon because we had 4 steps for array here we have many more of them. So all you have done for blocking on the pyramiding will likely be much more restricted. You occupy a lot more cache. Much can be done, certainly, with this respect. So we have to allocate all these intermediate steps. We have to initialize them at start. And we have the so-called butcher's tableau. Okay, I started with cache carp. I will be back to Rongekuta. Okay. Okay, so we have a small and nice butcher's tableau. You see CBA. And you can express it nicely in Fortran. And afterwards, okay, it is not so nice, but you apply the various items of the tableau in intermediate steps. And you recombine all of this to have the last value. Okay, so I did not implement it properly with pointer, so this is some inefficiency here, but not the most dramatic one. Please play with these to make them better. I am late. I have 10 minutes. Okay. Okay. So something that is not discussed in the implementation we have seen is what every scientist should do when given a physics equation or even a mathematics equation. You should non-dimensionalize it. You should set which are the natural scale of your problem, the natural scale of U, the natural scale of time, the natural scale of the V concentration. When you non-dimensionalize your equation, you see that your diffusivity terms have to be multiplied by the time step and the length step. So when we were looking at these, okay, Patra Kartunen, we had a good reason for it to be wrong. Onopuri, we had a good reason, but central difference, why did it fail? It is likely that it failed because well, so you see, if this factor, these factors are too big, it's not the diffusivity by itself, but the product of the diffusivity times the time scale divided by the square of the length scale that can get your program overheating and getting too big result, expanding above the concentration of 1 and getting things meaningless. So if there is a small error on V, and V gets over 1, so by the way, in the formula, this U0 is in fact set to 1. which shouldn't be the case. It means that we already have U is equal to U0. The scale is the default scale. So there is already some kind of discretization of non-dimensionalization provided. Okay, so something that I will tell you today so that you can see it at play tomorrow. This equation, in the end, when you get rid of the nonlinear terms, because, for instance, U is far, so you see that the concentration of U is almost 0 at first, and it spreads, it scatters. So when you are far from the center, you can use some small value development. On far from the center, you have some linear solution, approximate linear solution that has some dispersion relation. You can see that as you have some complex number, your wave vector of the wave at far will have some imaginary component, and so it's not only expanding, but the wave front is also vanishing exponentially, and you will confirm this tomorrow. So, any questions?
Yes, sorry, the mic was off again. Yeah, I just had a question about why specifically the last schema or was exploding. You said it was t over something, the time step over the square of something, but why would that be different depending on the schema? I don't understand.
Okay, so I have not a very good reason for why the central difference was exploding. Maybe I tried a different stencil on top of Runge-Kutta, and it was, I found some non-vanishing value because the scale of discretization was not proper, and I don't know why it got over the limiting value.
Okay, thank you.
So, so we can compare CK and RK. No. So, okay, with Runge-Kutta you have 5 fields instead of 2, and for cache carp, you have 7 instead of 2. More allocation. Larger butcher's tableau. But okay. Beside this, the algorithm is longer, but no more complicated. Not more complicated. So that's all for today, and thank you for your attention. So we will be back in 30 minutes.
We are 9.
Okay. So we are back again. Okay, so it's time after the break to do some memory wizardry with Mr. Malloc here. So I told you about how to profile your application with the memory, know what's going on in the allocation, how much you allocate, which time, when, why. So Sébastien, it's up to you.
Thanks. We'll come back to everyone. We'll come back to the memory world. I know you like it. You like the memory. I know. You will like it at the end of the week. So we'll come to memory allocations, why and how to profile. So yesterday we have seen a lot of things about CPU profiling, about the computation, etc. But what is happening during only the loops, let's say, in some ways. We'll now take a bit of back focus and looking at the application from the global point of view, how it is behaving in terms of memory management. So for this, I will focus on two memory profiling tools, MALT, which is here on the left, and NumaProf on the right, which are two tools I'm developing myself since my postdoc, since a long time now. I will come back on this. And I will present them, but to present some problems which can arise on your applications. So first, I will remind what is the memory problem we have today on large applications. I will list, of course, the competitor tools, which can solve also the same kind of problem. And then I will present MALT. I will focus a bit more on this one because it's more mature. And at some point, I will discuss about NUMA, architecture. About one concept, which is the NUMA architecture, non-uniform memory architecture, which is one of the concepts you have when you have multiple processors on the same server. We didn't discuss that yet, so we'll try to understand a bit how it's working in the machine. And for this, I will discuss a bit shortly, depending on the time I will have, NumaProf, which is a memory profiler about the NUMA aspect of what is happening on the machine. So let's go. Why I'm interested on this kind of topic, probably you understood already, but I made my PhD on memory management for HPC at CEA. And during my postdoc, I developed MALT at the Exascale Computing Research Laboratory in Versailles, where we were working around everything in HPC, where Macao has been developed also. This was the same team. And later, I derived it as a second tool, which is NumaProf, when I was at CERN. So these are two tools which are open source now and which I will present during this presentation. So just to come back to the problem, you have some servers today, some big servers, not so small, because now you can have up to 256 cores on one server. This is quite a lot compared to a long time ago where it was 16. 16 we were saying, yeah, big server. Now 256. You can put a lot of memory. You can find already some production servers where they said you can theoretically put up to 6 terabytes of memory. This is quite a lot. And of course, on such a server, you will not run a small toy like the Grayscott application, but more huge application, something more complex in general, which is written either in C, C++, Fortran, Python, or a bit of Rust. I list in green the first four because this is the one I will focus during this presentation. Of course, when you have a big application, it's very complex. You make a lot of things inside it. Mostly if it's in C++ with a lot of codes, and probably you finish with a lot of objects allocated to manage your application. It can go up to 1 million of memory allocation during the run for a few minutes. This is a kind of number which are quite often when you take a big one. And in addition, you have probably a lot of libraries which are underneath this application because you don't build everything yourself. You use some tools to build your code. And everything of this, you don't know how it's working inside. And in addition to this, in the research field, we have the short-term contract. So the people are entering in the project, going out, entering, going out, which means that at some point, keeping the global view of a large code is something very hard in practice. You might know how it is done at a point when you develop it, but 1 year or 2 years later, you might have forgotten a lot of things about how it is behaving. and probably miss some allocations which poses some problem of performance. In addition, we had the NUMA hierarchy, but when you have 2 processors or more in one machine. So this makes a lot of things to take in account. And we are now, as I was saying 2 days ago, about eating the memory walls. This is a paper which was written by Wolf and McKee in 1994, saying that at some point you will reach the limit of the memory speed. So you will compute too fast for your memory to feed the node. So I already explained this, so I will not take too much time here. So the problem has been fixed with the cache hierarchy up to now to get a fast access to your data, even if the memory bank access itself is slow. But if you take a large application, you can see something like this. So this is one of the numerical simulations I was working on at CEA, a large numerical one, an adaptive mesh refinement code with multiphysics, MPI, OpenMP, etc. Everything you put everything you can put in a simulation and you get it. And this code was roughly 1 million lines of C++. In 1 million lines of C++, of course, you made some mistakes at some point in the memory management, because you cannot handle this in an efficient way in your single head. And at that time, there was several memory allocators which were developed to support the multi-core architecture which were arriving. And for this, you have the glibc here, which is the memory allocator which is provided by Linux by default, which we called Douglea in principle, even if it has evolved a lot for the parallelism. And at that time, during my PhD, there was 2 memory allocators which were developed and were very nice, which are also today, gmalloc and tcmalloc. Gmalloc, this is done by John Evans, which is now working at Facebook and still maintaining a bit his memory allocator. And tcmalloc is a memory allocator made for cache optimizations done by Google. So we said during my PhD, maybe it's interesting to see how those allocators can impact the performance of this big simulation, which was doing millions of allocations and using a lot of memory. And you can see here that you change the memory allocator underwood the application, and when you take the state-of-the-art allocators, what you get is that gmalloc is taking a bit more time than the standard Linux one, which is not tuned for the architecture which are parallel and not NUMA. And tcmalloc is far slower. And when I say far slower, this is a slowdown of roughly 35%, not 1%. Where we can expect that changing the memory allocation pattern should not impact too much the performance. Here we have a really big gap. So I'm not saying you will always see this kind of gap. I will explain you in which context this application has run. It was on a large NUMA node, which was a prototype at that time. But anyway, this is the kind of thing we can see sometimes on some large codes. A large impact of the memory management part. You see here that there is some gaps with the green part. The green part is the user computation, so the time you pass in user space. And the orange part is the time you pass in the operating system. So we see that the different allocators have different behaviors here on the right. tcmalloc is kind of not efficient in user space, where the 2 others are not efficient in the kernel space. Okay. So I can say what is the benefits of gmalloc. Normally, gmalloc is a memory allocator which is very efficient to get a low memory consumption. It tries to pack as much as possible the memory footprint of the application. So it's nice if you want to pass on a server which has not enough memory for your application. But the compensation is that it takes more time to discuss with the operating system, to give the memory to the system, ask a new memory, give it to the system, asking again. Okay, so there is a high price which is explained here. This is why there is more operating system cost with gmalloc. And tcmalloc, in practice, it's done for caching. So it tries to keep the memory in the application. So normally, we should expect to have something faster because it keeps the memory in the system and not exchanging all the time with the operating system. But here, we will see a bit later that tcmalloc is not good on the NUMA architecture. because it don't take care of the NUMA aspect of the machine. It considers that the memory is fully uniform on the machine. And on my side, during my PhD, I was implementing another memory allocator in the MPC framework, multiprocessor computing, which is a re-implementation of MPI done by the CEA. And the goal of this allocator was to be parallel, as gmalloc and tcmalloc, to try to not consume too much memory when we need, and to take care of the NUMA. And we see that here I succeeded a lot in this run, because I was able to accelerate the application just by changing the allocator by a factor 2. Yeah?
How different does this look if you compare it to a unified memory architecture?
What you say?
Like this is a non-unified memory architecture, right?
Yeah, I will show the architecture on which it was running. It's a special architecture, so with 16 NUMA nodes, not a server with two CPUs. So it's a kind of challenging machine for the application.
But say that you would compare it to just like a consumer CPU today, like just a one CPU. How comparable is that?
It will be smaller, the gaps,
Okay.
of course. Here I'm presenting the kind of larger gap we can see. But just to say that if you make a mistake with the memory management, sometimes you can have a gap which is a factor 2. I see this several times. Most of the time, this is more 10%, 20%, something like this if you make a mistake. But it's already quite a lot for the full application. When you see that when you make vectorization, some people are fighting to gain 1% on this application, particularly the people doing the vectorization were fighting to gain 1, 2, 3% on the full application. So when you gain a factor 2 just by changing the allocator, you say, okay, I'm very happy. Also, you can see that by changing the memory allocator, you can change a lot the memory consumption of the application. So as I was saying, gmalloc try to pack as much as possible the memory. This is where it is good. And you can see that the gap is 1 gigabyte per rank here. Sorry, I should say it's per rank when you run in MPI. Where tcmalloc is more efficient in terms of speed normally, except for the NUMA architecture, but is increasing the memory consumption of the application. Myself, and the Linux implementation was kind of in the middle of those two worlds. So kind of making a balanced choice for that. Myself, I was trying to add, I mean, this is for a research perspective, but I was able to move from one profile to another, depending on where the application was. To say, if I need memory, I can slow down, I mean, shut down the memory consumption. And when I don't care, I can speed up and use more memory. That was my research. So the key today, from my perspective, of course, it's a bit biased, I would say. You need to understand the memory behavior of your HPC application, but also the others, if you want to get the performance. So for that, you need some tools, because during my PhD, I had not a lot of tools to look at what is happening in the application. The one I was saying, it was 1 million memory allocation in 5 minutes, something like this. And you need to guess what you should do with those allocations to optimize. Good luck, if you have no way to look at different aspects. So you can play by hand with some metrics, but if you have some tools, this is a bit better. So during my postdoc, I developed Malt, which is a kind of a way to try to express everything I understood about memory management to the user with a friendly interface. I succeeded as much as possible. Of course, there is some limits on the tool, but I will try to go on the different aspects here. So my inspirations for Malt was Valgrind and VTune, which were very nice with a nice graphical interface. Valgrind, I like it a lot. Valgrind plus Kakashgrind, as we have seen yesterday. So I try with Malt to get the same kind of feature, the same kind of interface in practice, done in another way, but for the memory usage. In practice, for the timing, you have a lot of tools for timings, but for memory management, if you want to measure the memory management of your application, you have very few tools in practice which exist today, at least in open source. So what you want to look at about memory, you want to look if your program a lack of memory, You go to the swap and you don't understand why your application was consuming so much memory. You want to find what is the hotspot in terms of memory consumption. You want sometimes to understand why your performance is impacted by the mallocs you have done. If you make too much, and when you see that changing the allocator is changing a lot the performance, maybe you make some mistakes you need to fix in your code. And a bit far away from what I really expose with Malt, if the memory layout is correct, because sometimes you can break your memory layout by putting some holes in the middle of your data, which might increase the memory consumption for some wrong reason, also degrading the performance. So the issues, when you have some issues about memory, you want to know some things about your memory allocations, track the mallocs. I want to know where the memory allocs are, which line in your code, which file and which line. You want to know the properties of the memory allocations, which one, what is the size you allocate, for example, and the lifetime. You want to detect some bad patterns, if they are bad for the performance. You want to find the leaks. Leaks, there is also already some tools. You know, Valgrind memcheck, for example, is giving you already the leaks, plus some others. There is a Dr. Memory, sorry, or this kind of tool. But I can get it in Malt, of course, for free. So I also have it. And you probably know that when you are doing threads, you have the TLS, thread local storage, which is a global variable which is duplicated for every thread. Okay. I personally know 0 tools which are currently reporting the memory consumed by the TLS, because most of them, they just ignore the global variables and the TLS also by default. In Malt, I try to report it. This is useful for Fortran, because the Fortran application, most of the time, they use global variables and not allocs. So let's take a small code example to see a bit the kind of problem we want to search for. So for example, we can search for a global variable or a TLS which has a large size. I have seen an example once. I was in a summer school about HPC, and the guy beside me was launching his own numerical simulation on the server of the school, and he was out of memory. With we had some nodes with a lot of memory, but he was out of memory anyway. So he said, yeah, why my code is blocking on this cluster? He was not knowing how to search. And I say, okay, I have Malt on my hand, so we can pass the tool on it and try. And we find in roughly 5 minutes that he had a global variables which was 6 gigabytes somewhere, which he forgot. So he made it for some reason probably small at some point, plus he modified some parameters, some define, which make it growing a bit too much. And he forgot it in this code and let it like this. And without any tool, you can search for a moment. If you have a global variables like this, good luck to find your problem. So with this kind of tool, you can find it immediately. You can search also for indirect allocations, where when you are calling a library which you didn't develop yourself, it can make some memory allocation for you. You didn't know because you didn't develop it. So might be good to see what it is doing. There is leaks. Here I allocate a pointer and I never free it. So I want to detect this kind of problem. Same for the global variables. I can allocate a very large dynamic variable and I want to find where they are coming from, where they are allocated, of course. And for the performance, you want to search also the short life allocations. Let's say you have a loop, for example, and you make a malloc, a very small computation, and a free. And you loop like this, malloc free, malloc free, malloc free, malloc free, which, of course, ideally, you need to put the malloc outside of the loop once and making your computation if you can. Let's say this problem of a short life allocation is quite simple in practice when you write everything yourself, but when you have some template library in C++, it can arise quite quickly for you without you noticed in practice. So with a tool, you can detect this problem relatively easily. So for the existing tools, of course, there is some. I lie a bit when I say there is nothing. There is Valgrind memcheck, you already know, for the leaks, which print you in the terminal in a long list of everything which is leaking. Not very efficient when you have a code of 1,000,009 plus some leaks a bit everywhere. You are a bit spammed with a long train of of output. Because it has no graphical interface in practice to analyze it, or at least no good one. There is Valgrind Massif, this time, which is making some snapshotting. So Valgrind Massif, every time the application is running, it's every, let's say, a few seconds, taking a snapshot and remembering which function has allocated how much memory at that time. So this is great because you have the time evolution of the memory consumption of the allocation. Plus, when you're at the peak, you can look on the call graph and find the top function which consumes the memory. So in some way, it answers the question of where my memory is allocated, which is something I wanted. But you get it with a snapshot approach, which means that if your peak rises up between the two snapshots, you just miss it. You don't see what is happening at this position. Also, remember that Valgrind is not parallel, so when you are in HPC on 256 core and you run something sequential, it's a bit a big limitation for us. There is also Google LAPP profiler. In TC-Malloc, there is a small memory profiler which is inside you can use. Personally, I never succeeded to have some really interesting results with that because it's just dumping a kind of call tree annotated with the percentage of allocations which are done. Some people say they succeeded to optimize some code with that. I know some people who say me, yeah, I succeeded with that to optimize my code. Frankly, I find it not very efficient in practice, I mean, in a large code, if you don't know already a bit what you search for. Of course, there is some commercial tools, so I will list a bit some of them. IBM has one, which is, I mean, both are very old, Purify++ and Ensure++. They are not free, so you need to buy them for a price which is not publicly said. One of them, which is, I forgot if it's Ensure or Purify, is running only on Windows, and the other one is running on all systems. But they are kind of think for a very old application which use which has a small memory footprint because they date from a long time and they didn't update it too much their interface. So they are great in what they provide in terms of metrics, but the interface might be modernized at some point. I would say it should be nice. But for the open source side, I mean, on Linux, we don't have access to them, so not interesting in HPC for most of the time. Yesterday, I also discussed about VTune. VTune has embedded inside a memory profiler, which just lists you the call tree annotated with the memory used by each function during the allocation at the peak time. So it's interesting to find, if you consume too much memory, to find directly from where the memory is coming, you get it quite immediately. So for this, it answers one of the questions I wanted to have. This tool is quite recent. It was not there 5 years ago, something like this, or 6. But it's running quite well, even if it's relatively simple. You also have a timeline here. You can select which part of the execution you want to look on and get the call stack according to the log, to the trace it is doing. So this is a tool doing a trace, which finish with a big, if you have millions of allocation on a parallel application, you will finish with a very big file to get your trace. This is one of the problems of this kind of tool. But clearly, it's well done to answer some questions for me. For those who are running on the Windows world, because we can work, we'll look a bit what Microsoft is doing sometime. In Visual Studio, not Visual Studio Code, Visual Studio, there is embedded in the Ultimate Edition, or now the official edition, a memory profiler, which permits you to profile everything in C++, C#, etc. Which is frankly relatively well done, a bit like VTune, providing the top, I mean, the cost of memory allocated for every function, etc., and some timeline. But this is not available for us in HPC because we are not running under Windows. So what I wanted to provide on my side, I wanted to take back exactly the same approach than Valgrind and Kakash-Grind without the emulation part, but in terms of semantic, I want to provide the same thing and the same kind of interface than Kakash-Grind. I want to map all the allocation on the source lines to say I want to see onto my source line how much memory I allocate on every line, because it's how I understand my code when I'm a developer. I want to search the memory leaks. I want to see the peak, the real one, not the snapshot approach, which can miss some peaks happening in the middle. So I have in Malt a special algorithm to detect lazily the peak and to account at the peak time how much memory each function is consuming. I want to count the memory allocation, because sometimes you have a function which is allocating billions of allocations, and maybe you should optimize that. The sizes, I'm tracking the minimum, average, and maximum size for every function to know if this function is allocating small blocks, large block, medium, or etc. And the lifetime to detect if the block is allocated for a long time, so I pay a price of allocation for something useful. This is all the metrics I want to have. On my side, I will not make some tracing, I will make some profiling, which means that I will try to project during the execution all the memory allocations, which are done point per point over time, on two axes. Either I project them over time to get a time chart, because an application is something dynamic, so I want to capture this dynamic of the application. Or either I want to project it on the call stacks, meaning on the code, to understand on my code which line is making which allocation. I'm currently also developing a tracing system in Malt to also have both view after that in a more advanced way if I want, in a second step, but it's not yet, it's done in the backend, but not yet reported in the front end. So let's go for the interface. So Malt is based on a web interface. I will come back on the interest of that just after. The interface I'm presenting here is just fresh new, because I just rewrote I made rewriting just all the interface by someone a few months ago. So it's a bit fresh. So there is still some problems to fix in the new one, but it's quite better than the previous one. So first, in Malt, you will find when you arrive on the web page, you will find a global summary. I will zoom on the different part after that, where you will find all the information of the run and some global statistics. So for the information, for the global statistics, you will find a lot of metrics, the physical memory peak, the virtual memory peak. So physical, virtual, I will discuss tomorrow what it is, or a bit later in the presentation. The requested memory peak, because it can derive requested. This is, when I say requested in Malt, this is everything which has been mallocked, everything I asked for. Because you know that malloc can add a bit of some padding in your block. So in the end, you can finish with a memory consumption which is a bit larger than what you really asked. So if there is a big gap between both, you can see that there is a mistake. The number of objects at the peak time, here it's a very small run, so maybe I should have taken a more interesting example. Some allocation pressure, so the cumulative memory you allocated. If you allocated terabytes of memory by saying at the system, I give you memory, I allocate, I give you, I allocate, and give you, I sum up all those sizes and it gives this matrix, cumulative memory allocation. If this becomes terabytes, it says that I pass my time to exchange the memory with the system, which starts to cost a lot. About the allocator pressure, I also have the rate, how much megabytes I allocate per second. If it's too high, again, probably the system is slowing my application. And the recycling ratio is how many times I made the up and down on the application. Again, how many times I reallocated all the time my peak. So you see here, there is some numbers in red. In Malt, I try to give you some hints, a bit like VTune. Some hints when I see that some numbers look strange. So this is a bit done like this with my feeling about those numbers. So this is not perfect, but it gives you a small warning saying maybe you should look on that. You can put your mouse on it and give some hints on what you should look in the details in the interface. You find also the global variables and TLS, how much they consume, which is the only tool which I know is reporting that. The leaks, this you already have with Valgrind, but I have it here. And the block size to know the smallest size you allocated, the largest one, and the average, just to understand how you your application is behaving. And you can get the memory consumed by Malt itself also, because sometimes Malt also add up some memory, because I need some memory for my own running. It can be a bit large sometimes depending on the application, so I print it how much I consume myself. You can get the per thread statistics also to see the dynamic. Is the thread 0 is doing all the memory allocation, or is every thread doing the memory allocation? Is one thread doing the allocation, another one doing the free? Because when you develop a memory allocator, you know that it can pose some problems. So this thread table, it's interesting to understand the dynamic of the application, but not to optimize. Most of the time, I never made some optimization with this view, but myself to understand the behavior of the application is interesting. And the more interesting view of Malt is the source annotation. This is a bit the core part of the tool. So here, this is the same kind of view than Malt or than Valgrind, Kakashgrind, sorry, or VTune in some ways, made in I found a bit friendly way. So you get on the left the list of functions with their metric. So you can select here the metric you want to look on. I will show the list after that. And you get the annotation for this metric. Here, this is the allocation count, so the number of allocation done on this line. And you see that the annotation is colored for the hotspot in red and in blue for the rest, which cost less. So you can focus normally in the red part to look on if there is a problem. In the bottom, you get the call stacks. So if you click on one annotation, you get the call stack on the bottom to know how you reach this position in practice in your call tree. So for me, this is, when I'm using Malt, most of the time, this is the view I'm using to dig in the code. When you click on an annotation also, before going to the call stack, when you click on one annotation, you get the details about this allocation, this location, number of allocation, sizes in terms of average, minimum, lifetime, etc. The local peak, this line, how much it has consumed as much as best during the full execution. This is what I call local peak for the peak attached to a location particularly. You will see that Malt reports you a lot of metrics. They are organized a bit in groups. So some metrics about the block sizes, so the allocated memory in sum, the allocated number of allocation, so count. The minimum size, if you want to search the small blocks where they are, you can use this metric. If you search for the largest one in the code, you can use max alloc size. You can track the free. I know Zero tool which permits you to find the free in your code. Most of the time, they permit you to see where the malloc are, but not the free. So I made it. The peaks, how much each function is consuming at the local peak. So for every function, how much they consume for their own peak, or for the global peak when the application is consuming at the top. You can find the leaks also with the source annotation. This is easier than Valgrind because now you can dig in the code directly to find the leaks at their position. This is a bit easier than having a kilometric log in the terminal. You can track the realloc, and since 1 year, you can also track the mmap and the munmap directly. So the lower, for those who are not familiar with the memory management, this is the lower part of malloc to get the memory from the operating system directly. I have a student who made me a nice view also at some point at CERN. Who was Jeffrey. He made a call tree annotated, just like you have in Kakashgrind. So you can dig directly in this call tree, and you can click to go down to walk over the tree. Again, I try to put in red and with some big arrow the hotspot in terms of the metric you have chosen. Of course, you get some chart over time to get the dynamic of the allocation. So the virtual memory, the physical memory, and the requested one here in orange. So normally you always see that the virtual memory is higher because the virtual memory is what you should have at max. The physical memory is what you consume really. in terms of pages. We'll come back on this kind of metric tomorrow to detail how it's running on the operating system. And the requested memory is what you asked with malloc in practice. You get the graph about the allocation rate to see that sometimes you have some phases. Here I have an application which is doing mallocs here in orange, then freeing the memory a lot, then making again a malloc cycle, then a free cycle, then a malloc cycle, then a free cycle. So like this, I can understand the dynamic of my application. Ideally, I should see 2 peaks, 1 peak at the beginning, which is I make malloc at the beginning, and a peak at the end, I free at the end. This is the best. But most of the time, you see that you have something in the middle. Of course, when we speak about malloc, there is a large literature about the allocation sizes, the size block allocated in the allocator. Most of the paper about the memory allocation is speaking about what size you allocate, what are the distribution of the size of the application. So of course, Malt is giving you this chart with the number of allocation and the size it refers to. You can notice on this chart there is something strange. You can see that most of the allocation for this application is 16 bytes. If you remember that to point a malloc, you have a pointer of 8 bytes plus an header of 16 bytes to manage the allocation. You have probably doubled your memory just to manage the 16-byte block you allocated. This is not good. Okay, so if you see a peak like this with a very big peak with very small allocations, it's probably that you have a problem with the memory consumption of your application, probably. Maybe you cannot do something else depending on your algorithm, but you have to look at it. For the global variables in the new graphical interface, it's presented that way. You get first the top 10 global variables, the one consuming the most in your application, with an annotation if it's a TLS or a global variable. You get the virtual size and the size, for the TLS, the size of one element and the size multiplied by the number of threads, because you duplicate the variable for every thread for a TLS. So the size it has consumed. And for the global variables, I'm able to give you the virtual size, so the size you requested, and the used size, so the size you effectively used. Because sometimes you allocate a big variable and you don't use it fully in your program, so you can detect it with Malt in this case. As in some views of Kakash-Grind, you get a kind of a box view presenting for every global variables the size of the box, depending on the ratio of the variable concerned. So you can quickly see which, get a representation on how your memory is distributed over the global variables. You can get them over a bar chart. This one is an old representation I had originally in Malt, but sometimes it's still useful to have it, so I kept it. This is a bit all the views you have in Malt, which is already quite nice. Quite a lot of work to get it. So I will now try to show you some use cases to see a bit some examples of what we can detect with Malt. There is some question on Discord. Thanks. Question on Discord. A lot. Not loading for me. This is before. Do you also have insight about what kind of memory is allocated? If it's a virtual memory or a physical memory, not yet. I'm working to have it inside. I have it inside my backend, but I don't yet reported it in the graphical interface. So no, for now, not in the graphical interface, but it will rise up at some point if I have time to finish the implementation. Slide 24, for those familiar with memory management, well, you are here to learn. Yeah, true. To get the details about memory management, I will have a full courses about the operating system, how it manages the memory, how the caches are working tomorrow, Friday. So of course we will understand a bit in more depth what I'm saying here. Sorry for the order we made the thing for the school. And someone is asking a question, so I will just wait to get it. For the virtual memory, I will come back a bit on it for the next. Is it possible to use malt for MPI programs? Yes. I will show in the example just after that how to use it. There is a -- MPI option to pass to malt when you're running in MPI. The only thing is that you will get one profile per MPI rank. So you will have to dig in all the ranks, but most of the time when you are in MPI, you are interested in what is happening in one node, not in the global application where it's run. You was referring to RAM, cache, etc. Yes, again, RAM, cache, etc. I will explain in details while speaking about the operating system on Friday. Thanks, Luca, for the question. Why the memory management is important in HPC performance? Exactly for the example I was showing at the beginning. And L1, L2, L3 cache, malt is not looking on the cache, it's looking only on the mallocs. So I don't care about the caches in malt. This is not the goal of the tool. So we will discuss more in details on the cache, how it's running again on Friday. When in Friday, it's Friday at the end of the day, no? We have the timetable. At program of the school. Friday, it will be at the same time at 4 o'clock in the afternoon. Thanks, Giordano. Some other questions are coming. Some questions here before I continue also? Is there some way to profile this kind of allocation? You mean so this is Lucas about the cache. So the cache is not doing some allocations. It's the CPU which is deciding. I will explain on Friday. This is the CPU which is decided what is in the cache. So yes, if you want to look at it, you have vtune with the hardware counters. Not easy to look at, but in some ways you have the hardware counter to look at it. Yeah, so with vtune and perf you can get it. This is the kind of tool for the cache you need to use. Or Valgrind with the cache simulator we have seen yesterday, cache grind. If I use Intel compiler, GCC, and VHPC compiler, should I compile malt with the same compiler? Ideally, yes, because malt is written in C++. In practice, sometimes it's working depending on what you are using in your code, because malt is too tight, is not strongly linked to the C++ version. But if you want to be sure, because I have seen some glitch sometime, prefer to compile it with that compiler. But normally compiling with GCC and using malt on your application should run. So maybe you can try by default. Thanks, Isabel, for the question. So maybe I will come back to the examples. So here, this is some examples I encountered at the Exascale laboratory when I was developing the tool directly. The first one is a Surfax application, AVBP, a CFD simulator. Here, it was a student who was developing a GPU version of this code at some point. And he was noticing that because he was able to grow the problem because the GPU were far faster than the CPU implementation at some point. So he was running on a bigger problem than on one machine than what the code was doing commonly. And he noticed a small problem is that at the start of the application, the initialization time was roughly 3 minutes or 4 minutes, which is not very nice when you make some simulations. So he was questioning himself and searching a lot. He was searching for a few weeks from where this time was coming, and he was not finding any solution. So he came to me, and we passed some time to pass the application on malt, which was just fresh at that time. And we looked at the code, and we directly see this graph, the allocation rate, so how much memory bandwidth I was allocating per second. So if I'm allocating 1 gigabyte per second, it means that every second I was asking 1 gigabyte to the operating system. So the operating system has to give me 1 gigabyte per second. So when you see the graph here, it's going up to 6 gigabytes per second. and in continuous for roughly 200 seconds, so something like 3 minutes. The good point with Malt is that we were able to find from where it was coming, because with the global metrics about the amount of memory allocation on one line, we can directly find that one line is allocating 57 gigabytes of memory by summing all the memory, not instantaneously during the execution. And this is these two lines here. So there is an if statement, an allocate, do something. So we are copying an array, and deallocate just after that. So allocate, copy, free. You might know the pattern it is. Someone guess what it is in C? Malloc, free. Malloc, copy, free. Most of the time, this is a realloc. So here they are making a realloc by hand, so increasing the size of the buffer, copying the old one in the new one, which is bigger, and freeing the old one. Of course, because in Fortran, you have all the allocatable function, but not the reallocate. So you should do it by hand, because you are forced to. So this is what they did. And in practice, when we looked at what they did it by making +1 every time. So adding one element, so allocating a new array, copying everything, and doing that way, +1, +1, +1. Which is very costly, because you copy 100 megabytes of memory each time you allocate one element. So of course we looked with them to change this behavior and make so not changing the pattern because they needed to reallocate at some point, but to make it by bucket, to increase the size of the vector by 100 elements by 100 and not one by one. So by doing that, the application was at the end, it was something like 10 seconds to start instead of 3 minutes. This is a great optimization. We found it in a couple of hours, where before they were searching for days from where it was coming from. So this is the kind of thing you can detect quite easily with Malt. I will give another example, again in a Fortran application. This time this is Coria ELS2, so combustion simulation, so real code. This is something for myself. I like to look the thing on real codes and not on toy apps, because you have a lot of things to understand when you are looking on a big thing. You remember the chart I have shown before, the 16 bytes, which were allocated the most. This is this code exactly, and I was searching from where those allocations were coming from. This 16 bytes allocation, which are here, and they are following the tool. I found that they are all coming from this line in Python, in Fortran. Sorry. So this is a strange line because for those who are not familiar with Fortran, percentage, this is a dot of every other language. So I'm accessing a member of a struct, which is an array. So I'm accessing to the member, which is val, which is a table, and I'm copying one table to another table. Okay, those tables already exist. So normally there is no allocation. So why is doing some allocations here? So myself, I discovered this while I was implementing the tool. So I say myself, I made a mistake in my tool. This is reporting something totally wrong. So I passed, 1 week to search a bug in my tool. And after 1 week, I said myself, no, but there should be a real allocation somewhere in this code. This is not possible from what I see in my own one. And clearly, yes, in some situations, Fortran can generate some mallocs for you in a loop like this. So I forked the old compiler from Intel, so I don't know the new one. The old compiler from Intel with some options was able to fall back on the same behavior. And with Fortran, there is some options to tell him to not do that. But by default, it is doing it in this case. And yes, at some point, you can detect with Malt that your compiler has made for you some memory allocation at your place. So this is interesting to look at. And this is exactly the example I was saying about the short-lived allocation, because here it's a malloc and free. I'm making malloc, a small copy in memory, and then a free. And this is a malloc which is very short, so not a long one. 16 bytes, it's not costly to allocate, but anyway, I'm calling malloc and passing a bit of time in the function to make it. And here, for example, so this was a long time ago. A long time ago, many people were saying, yeah, Fortran is very slower than iFort, etc. But in this case, most of the difference on the benchmark were coming from the fact that the malloc was there. So the compiler was not so bad in practice, it's just that it was introducing some mallocs where it should not. I don't know for today because I don't follow if today this is still the case, but just to show some examples. 1 byte allocation. So this is fun. Myself, well, the first time I passed malt on one application, I seen that, I said, come on, 1 byte allocation. But every time you pass malt on some codes, you found some of them. Alors if it's just some, it's fine. If it's a lot, frankly, maybe try to take care of what you're doing. Most of the time when I see that in a real code, it's via the template system. Via the template system, sometimes you can finish with 1 char allocated in your template or a boolean, which finish with a malloc of one element. So how to use malt? Just to, yeah? Question? Thanks for stopping me. I don't have the notification, I should have one. So question, can this tool help to assert whether the RAM or the GPU memory might be more optimal? The RAM, yes. The GPU, I'm working to get the GPU support, but I don't yet have it. I have a prototype, but not yet operational. So it's not in the official release, of course. Higher order scheme require more temporal variables. Does malt allow for a precise quantification of the memory cost induced by this scheme compared to lower order schemes? I'm not sure to understand your question, Mamadou. I mean, in some ways, what you are saying is that when you are using higher order, you get more variables, like for the Runge-Kutta presentation from Vincent before. So of course, in malt, you will see that there is more allocation at the place where you are doing the arrays memory allocations. So in some ways, yes, you will see that in practice. If the question is, will I see that in my loop I'm using too many arrays? No, this is not the goal of malt. Even if it could be interesting to have such a tool. Mireille is posing a question, so I'm waiting to get it. If you use GPU, you don't have the choice usually. You use GPU memory. The difference could be the strategies of copying the data from the GPU and the main RAM. NVIDIA provides tools to analyze this stuff. Yes. So what I want to have with malt, again, is to get the memory consumption and from where it is coming. This you have kind of with the NVIDIA tools. But if you want to say this function, how much memory it's consuming, you get it. You need to search a bit in the presentation, which is done in Nsight. But true, this is a bit redundant with the NVIDIA tool. But the good point of malt is that it's open source, and it's when it will run also on AMD GPU, which is not the case of NSYS. But yes, it's redundant to what the others are doing. So for the usage, the only thing you really need to use malt on your application is to compile your application with -G. Require. It's require if you want the source annotation. If you want the graphs, etc., the time chart and the numbers, you can skip that. You can skip the -G option. Malt is only for app profiling. Yes and no. It's mainly for app because I'm tracking malloc and free. I'm tracking also mmap and mnmap. So yeah, app in some ways. And I'm reporting the global variables as I'm saying, so not only the app. The only thing I'm not yet reporting is the memory used by the binaries themselves. This is not a big work to make it, but I don't yet made it, to report in the graphical interface how much memory is used by the binaries, which sometimes can be very big. I have seen some. NumaProf, I will come back on this just after that, but NumaProf, it's about CPU, not GPUs. And Malt, the GPU is just fresh, so normally I will have the GPU support for AMD, but I don't know, I don't have a date for delivery now, so consider that it's not there yet. Did 1 byte allocation create a problem, Guillaume? No, if it's not too much. I mean, if you have just a few, it's not a problem at all. Now, if you start to have millions, you request for one byte of memory, you get a pointer of 8 bytes plus an header in the block of 16 bytes, which means that for 1 byte you requested probably 24 bytes of memory. So if you make it a million times, you start to consume a lot and to kill your performance about the caches, which I will show an example on Friday. Thanks, Guillaume, for the question. Another question is popping. You like the memory, you see? A lot of questions about memory. That's a complex topic, so there is a lot of questions to ask. So, came back to the usage. So I say compilation with -G, ideally if you want the source annotation. Then you run, just like Valgrind, malt./myprogram. Simple. No, not difficult. And it will produce a JSON profile file, which you can open with malt-webview. Sorry, I have a -I which is not there anymore. You open your the profile file with malt-webview, which open a small server on which you connect on and get the graphical interface. Myself, opposite to Valgrind and Kakashgrind, I made this web interface because when you are running on a cluster remotely, you always have some troubles with Xon's graphic tools, because either you forward the graphical interface via your SSH, which make your interface a bit having some glitch and very slow. Either you copy the profile on your machine, but you don't have access anymore on the same sources and on the remote cluster. The good point with Malt is that you run the server on your cluster, so have access to all the sources as they are on the cluster, and the rendering is fluent on your laptop directly locally. So in practice, this is quite efficient. It's working in containers also. Thanks to that, we will be able to make the demo after that. If you are running on a cluster, you can SSH to forward the port locally. So you say SSH your server, and you say -L for local listening to redirect the 8080 port from localhost on the, to redirect locally on the 8080 port what is at localhost port 8080 remotely. Question again. Thanks. Why I don't have the pop-up on top when I'm full screen? Can I find allocator issues with Malt? You mean a bug in the memory allocator itself? No, this is not the goal of Malt to validate the allocator, Stevenson. It could be very interesting, but no, this is not the goal here. The goal is to understand how I misuse the allocator. This I can find. I'm not making what Valgrind memcheck is doing. So if you make a free on an address which is not the good one, I'm not there to report that. Probably I will crash due to that. I tried not most of the time if I don't find. But Malt is not there to make validation. It's less there for the performance aspect. Thanks for the question, Stevenson. If you are running on a cluster, on a server which is used remotely, instead of opening a port, because if you use a port on the remote cluster, it can be connected. Some other user can connect on your Malt, which is not very nice. This is the problem of the server approach. In practice, you can use the socket, the Linux socket protection. Where is my mouse? You can use the Linux socket protection. Where Why it's bugging? Oh, get some troubles. Why it's slowing down like this? Freeze? No. Come on. Come on. Sorry. Demo effect. Memory consumption, probably. Why it's freezed? Yeah, it's okay. I don't know. So instead of using a port, you can say -- port equal a file, so a socket file in your local cluster. And remotely via SSH, you can access it by saying locally on my machine, on my laptop, I'm using the port 8080 locally, so no one can access it. And on remote, I'm using malt socket. So here, nobody can access your malt remotely without you notice. You can also export now, since the last version, this is a new feature since the 1.6 version of Malt. You can also make a static export here. You can use -- static, giving a directory where it will generate a static version of the web view. You will miss the source annotation because you cannot dig anymore in the sources, but all the other metrics will be there. This is interesting if you want to send the report to someone. By default, it embeds also the profile in it, which sometimes the profile can be big. So you can say embed profile none if you don't want to give the profile to the person or to just put the page online for some people. And if you want only the summary page, only the first page of the tool, you can say static summary equal report. So this is useful if you want to send it. So in the report, it will create an index.html, the favicon, and a static profile.js plus the JSON profile compressed if you enable it. So it's good if you want to share it by mail with someone who don't have Malt, so you can get directly the interface to look at it. So let's currently I spoke a bit about C, C++ world. So Malt is running for C, C++, Fortran, Rust by default. All those languages are supported natively. And you know that today, of course, in HPC, people tend to use Python for a good or a bad reason, but they tend to use Python. The most common case is to have a Python script which is calling some C code via some libraries compiled to be efficient. So let's say in this kind of way, Malt was running quite nicely already originally, because I know how to analyze the C. So I was showing everything which is in C natively. But for the Python part, I was showing the part which is happening inside the virtual machine of Python, which is not so nice, because it's not what you expect if you want to get a profile. So there is some tool which exists about Python, which are Memray. Memray, which is a very simple tool, but very well done, I would say. The guy has made a very nice work. It's someone from, I forget the company. You can search. He made it very nicely. So you can have some reports with the flame graph at the end, and a kind of perf stop or h stop if you want, which permits you to survey a program running dynamically in real time. So you can get the hotspots, so the functions which are consuming the most memory directly by looking on this tool. Anyway, it's a great tool, but relatively simple in the number of metrics it's exposing. So you can look on it quickly, but it's not as deeper as Malt in terms of as metrics. Another one, which is my, the other person in the US working on memory management, which is Emery Berger, who has made 2 years ago Scalin, which is a memory profiler, a profiler in Python to profile many things, and memory, by the way. Scaling is nice in some ways because it's focusing only on the hotspots. It will show you the memory usage for the location, and pinpointing the hotspots directly by showing you some annotations on your source code. This is done only for the hotspot, not to look on the code globally. So already this is quite nice, but it don't answer to some complex question when you have a large application. But for the hotspot, I should say it gives some nice answers, which is what you want to look most of the time. So last year, 2 years ago, thanks to INRIA, University of Grenoble, and the Pôle Innovation of the Grenoble Alpes University, I was financed for 1 year to add the support of Python in Malte, because I thought it was interesting to have it. So thanks to them, since last year, we get a version of Malte which has a Python support natively. So you can instrument Python directly with Malte. And this is also with this finance that I was able to rewrite completely the web interface to make it a bit more modern. And also to get a nice documentation, which was not there before. So now on the website, you get a good documentation with some examples on how to use the tool. Very nice. I can improve it still, but so to support Python, you can support. You need to build Malte. Malte is not available in pip, so you need to compile Malte against Python natively on your machine as you compile it normally. You just need to have the python-devel package installed on your machine to get it. And once you compile it against one version of Python, there is no problem. Malte can work with all the other versions of Python which are supported. So you compile it once for having it for any version of Python you will have on your system. So it's the current version which are supported are from 3.11 to 3.14, and also the Anaconda environment in with some care on the way to build Malte. This has required a lot of work because this is not so simple in practice. In Anaconda, the only thing to take care is that Anaconda is providing again the libc++ version, which is not compatible sometimes with the version of your system. If your system has a version of C++ which is more recent than the one in Anaconda. So in this case, you need to take care to compile Malte with the C++ version which is inside Anaconda. This is the only requirement you have. So in terms of usage, I'm still searching the good way to use Malte on Python, because the problem on Malte of Malte on Python is that Python is globally making one memory allocation for every line, which is not the case in C++. So of course, Malte is a bit stressed a lot by a lot of things to analyze. So already in terms of overhead, it's quite heavy, but also in the web interface, you get a lot of information you need to dig in. So I try to simplify a bit the view, but I'm still searching the good way to work in this language. So normally in Malte, to use Malte with Python, you can use just Malte-Python, giving if you want the Python interpreter you want to use and your script. Simple. You can give, if your script is executable with the shebang inside, you can just give directly the script below Malte-Python. Malte has several profiles. I was forced to do that due to the fact that I received too many mallocs in Python. Otherwise, the tool explode in flight. So there is a first mode, which is ignoring all the imports, because most of the allocation when you are running a Python program are coming from the import, because it's importing all the packages and making tons of allocations, which you most of the time don't care, because you cannot do anything about them. So by default, I don't show them. I hide them under a fake function, which is import. And if you really want to have the full profile, so profile everything in Python, you need to use a -- profile Python full, and you see that there is several profiles which I provide here, depending on how deep you want to go in your analysis with Malte. So there is a first profile which is Python default, which is showing only the Python, not what is happening in C. the C allocation are projected into the Python stack only. So we'll not see what is inside the C part. Where if you want to see both worlds, the C part and the Python part, you need to use Python full profile to get everything, because it's more costly for me to get it. You can get Python no stack, because sometimes it's interesting to be fast. Here it will not reconstruct the stack in Python, just giving the metrics to get the charts, etc. And in last resort, because I tried to pass Malt on PyTorch and scikit-learn, which are making tons of allocations. There is no limit there. There the overhead is quite high in practice, so I had to do sampling. You remember the sampling I was saying yesterday about the profiling? I have a sampling method in Malt, so you can say profile-python sampling to get a sampling approach in Malt. So look only on the first top function in this case, because the other one will be not allocated to the right line. But for the top function, it's quite efficient in practice and very faster to get the performance. So I would say, for me, the protocol I'm using now to run on a big program, if I have a big Python program, we're using PyTorch or this kind of stuff with millions of allocations, billions sometimes. I'm first passing with the profile no stack to get a view with the chart and get the first view on the program with a short amount of time. Then I'm passing in sampling mode, then the default mode, and then full mode to go deeper and deeper in the analysis. I'm not yet sure this is the best, but I'm still in the process to understand what is a good way to profile this thing. Just by the way, about the sampling, Scalin is doing also sampling, because they had the same issues as me for PyTorch and scikit-learn, that they are making so many allocations that you are fluid in practice in the tool. So let's stop here for Malt. I don't know what time it is. Yeah. I will move to NUMA, non-uniform memory architecture. So I will explain what is NUMA. So when you have one CPU, it's easy. You have one CPU, then the RAM allocated to this CPU. But when you have two CPU, what you do? Either you put all the RAM allocated to one CPU, or you distributed the RAM, the banks of the RAM, to different CPUs to balance a bit. So in practice, this is what we do today. But you have a small problem now, is that if your CPU, your program is running on the CPU 2, and it needs to access some data which are stored in the CPU 1, you will pay a price because you need to pass by that link here between the two CPU. So if you don't take care of the placement of your data on a NUMA architecture, you will probably pay a price while running your program. Alors, when you have two CPUs, this is quite fine, but you can have 4. If you have a machine with 4 processors, this is something we had more in the past than today. You can have some programs which need to be optimized on this. And if you make a mistake in this kind of machine, either you get lucky and you get a crossbar in the middle and you can take this link to go to the far memory, or you have to make in two steps to get access to the far memory you have on the machine. And in this case, you pay again a higher price because you jump 2 times to get access to your data. You can make even worse. Me, during my PhD, I was running on a machine, the Bull BCS, which was a machine with 16 processors on the same machine. This is the performance I was showing with the big application. So a machine which is not common at all, very hard to use. 16 processors, and there, if you are on this processor and you go to search data from the processor on the remote, of course, you pay a high price because you make many jumps to get access to the data. So there, you need really to take care in account the data placement in your program. You can say the NUMA is only for the people having 2 processors on the same server. This, for the servers only. On your laptop, you never add 2 CPUs on the same laptop. But nowadays, you also have inside the CPU many multiple NUMA domains. because there is too many cores to place in the CPU. You cannot place them in a single NUMA domain to access to the RAM. This is too hard to do. So most of the vendors today, they split also the CPUs in NUMA nodes inside itself. So even with one CPU, nowadays you have some NUMA domains. Historically, there was also some people trying to put some fast memory inside the CPU itself, the MC-DRAM for Intel, which is some memory with fast bandwidth like for the GPU. So you had again a new NUMA domain specially done to access this memory in specific, which they call HBM, high bandwidth memory. So you see that nowadays in most of the architecture you are in a NUMA context in practice quite often, which were more rare in the past. So how to work in a NUMA domain? First way, you make such that your process is running only on one NUMA domain. Easy. In this case, the operating system knows that your memory should go in the memory of the domain which is related, so you will place every data if it fits in the memory, on the memory attached to this NUMA domain. Trivial. For this, you need to pin your process so it's not moving from one core to another. If your process is moving during the run to the next NUMA domain, of course the data will stay on the first one and you will have a problem. So on a NUMA machine, ideally for the performance, you need to pin your threads on your NUMA domain so it's not moving elsewhere than where it is. If you are in MPI, most of the time you are doing that. You make one process on every domain, and inside your process you split with threads inside the domain, and you pin, and you avoid any problem. So in this kind of case, no NUMA problem to take care in your code. It's done automatically by the operating system for you. The problem starts to rise up if you want to run in this situation, to run one process which is balanced over two NUMA domains. Because in this case, the operating system cannot guess what you are doing in your application, and it's up to you in your code to take care of your NUMA thing. Yeah, question? Can you take the microphone?
Yeah, I just wanted to ask if there's like some way to just duplicate the data in both the memory on both sides.
Yeah, there is what they call the interleaving mode. So either you can ask it in software to interleave and put half of the data in one side and half of the data on the other side.
Yeah.
Or you can do it in hardware. Most of the architecture which has a NUMA domain, you can put in the BIOS to say the CPU will by default balance everything, so there is no NUMA view for the application, for the system also. This is slower in practice because you are less optimized, because you will use a link in between all the time, but you don't have to take care of yourself of what it is happening on the machine. So this is a kind of medium approach, but if you really want to take the performance out of the hardware, you need to take care of the NUMA placement.
Okay, thanks.
So here it's the kind of strange road to take. If you want to play with the NUMA part, you enter in a world where you need to take care by yourself on things you probably don't want to take care about. Anyway, we'll see now how to take care about it. And good luck if you go there to see how it's working. So here I will introduce one concept about the memory management part. I will come back on this also on Friday in more depth. I will introduce it a bit simply here. This is physical and virtual memory side. In practice, when you allocate some, you play with some addresses in your CPU, you play with virtual addresses. This is here the address your application are seeing and playing with, is a virtual world. And in practice, you have the physical addresses, which are the addresses in the banks, the addresses in the memory itself on the hardware. And there is a correspondence which is done by the operating system between both of those domains. And the operating system is responsible to split this domain in what we call pages. A pages is an element of 4 kilobytes. So a block of 4 kilobytes, which is matched between a virtual address and a physical one. And the operating system is responsible to put those links here, to attach a virtual page to a physical one for all the domain where you play with your memory. There is a good point here that it's, you will see on Friday what are the interests of this methodology for the operating system. This is one of the most beautiful things in computer science, from my point of view. It's solving a lot of problems in one single idea. We will not discuss that here. But let's say that in principle, when you are allocating a new segment, when you are making a malloc of 1 GB of memory, for example, by default, your segment will be virtual. At the start, there is no physical pages mapped on it. And when you will make the first access, the first touch, we say, the operating system will say, you are accessing to this element, so I need to give you some pages. And this is at that time that the operating system will say, hey, Fred, which is accessing to my page, where are you? The thread will say, I'm on the NUMA node 1, so the operating system will give some pages on the NUMA node 1. Okay? If the thread 2 is on the NUMA node 2, the memory will go to the NUMA node 2. Okay? Now, if the thread 3 is moving sometimes on NUMA node 1, sometimes on NUMA node 2, and is not pinned to one thread because it can go everywhere on the machine, what the operating system is doing? Kind of random. You don't know. Either it will go in one way, either it will go in the other way. Most of the time, it will be where the thread is at the time it makes the first touch, and next time it will be to the next NUMA domain, and another page which will be touched will go to the other way. So there, you see that the problem of the NUMA domain is that the semantic to say where the memory is kind of indirect. It's not you which is saying in your code, I want the page to be there. It's when I make the first access to my data, it will go there, which is a bit subtle in practice. So let's take an example. You know OpenMP. So most of the time in OpenMP, you make a pragma OpenMP with a loop, making some operation in my array. And at the beginning, when you just made your allocation, you make a memset or a loop to initialize your array. Okay, this is common to write it like this. What is the mistake here? Someone see it? There is a performance mistake and a big one here. Yeah?
That you overwrite it? No? Or...
But I initialize my data, so this is normal. I write on the data, then I'm making some computing, so here just an increment of the value. So this is normal that I'm modifying the data with threads. But in terms of performance, this will be very poor. Yeah, because my thread here, the memset, where it is?
On one thread.
On one thread. Okay. The way I made it, it's on one thread currently. So probably NUMA node 1 or 0, depending on if you start to count to 0 or 1. It's on one NUMA node, and it will map all the memory to one NUMA node. Then the threads, what they are doing? Every thread is accessing to the thread which is on NUMA node 1 will access to NUMA node 1, and the thread which is on NUMA node 2 will have to access again to NUMA node 1. So you will use the link all the time to access the memory. So in practice, if you want to get a good performance with that, you need to make the same access at the initialization time than in your computing time. So just use also a pragma OpenMP for loop on the initialization loop. Okay, if you do that, your data will be half on the NUMA node 1 and half on the NUMA node 2. The performance gap can be quite big. For this example particularly, if you run it with a big array on a machine, you get exactly this kind of performance, a factor 2, possibly. So at some point, you can say, yeah, but how I detect that I made a mistake? Because this is implicit. I didn't write something in my code, so I cannot see the thing explicitly. So I got a friend of myself, Otman Bouzi, which was working for Intel at that time in the Exascale laboratory at Versailles. And we were discussing, he was saying me, but yeah, but with what you did with Malt, cannot we derive the tool to make something to detect the NUMA accesses and to detect if we make something wrong with the NUMA aspect? And we were thinking together and discussing a lot. And in practice, it appeared that it was possible to patch, to reuse a part of MALT to make a tool like this to detect two things: where we are making wrong accesses in terms of NUMA, and from where they are coming from. So where are the first touch made, and the wrong one. So this was a kind of Christmas letter he made to me. Please make me a tool to make this. I mean, we were discussing together, so it's more for joke. So I made NumaProf when I was at CERN. I derived MALT for most of the things. So it's taking the same part from MALT, which is the web interface, the source annotation, the global metrics, the same logic in practice. The only thing which is different is the instrumentation, because there I want to instrument every memory accesses now. So I need to every time there is a memory access, I want to say, hey, stop here. Where are you? Where are you, memory access? Where is the page? So I check the access the page, and I check if they match. And if they don't, of course, I say this is a wrong access. For this, I wanted first to make the instrumentation with Valgrind, but Valgrind, of course, is not parallel, so on a NUMA architecture, no interest. So I used PIN. PIN, this is the software which is used developed by Intel to make some parallel instrumentation of a code. This is exactly what they use in bottom of VTune and amplifier we have used yesterday. So I made myself injected into PIN to make all the instrumentation of the code. So this means one thing is that MALT is working only on x86 and x86 64 architecture and not for ARM. There is another tool like this which works on ARM, but I don't yet, I don't have the time to make the port myself. So what I want to track with that, I want to track the remote accesses, where I make a remote access which is wrong and I need to fix. If my access is local, this is to check if it's green and valid for me. MCD-RAM if I have an MCD-RAM access. Where is the page is pinned, because the page, if I touch it in a wrong way, the page is placed randomly on the machine. So I want to detect also this pattern, the OpenMP problem I have seen before. And if the thread is pinned, if the thread is moving from one NUMA node or fixed on a single one. There is one thing with MALT, with NumaProf, sorry, contrary to MALT, I cannot get the call stacks, because otherwise I get an overhead which is far too high, because I instrumented all the memory accesses. This is quite not cheap to do. So the overhead of NumaProf is more factor 40 in terms of slowdown. This is a comparison if I would have done, so this is the slowdown of MALT on a 256 core server, which is a factor 60, where if I would have used the Valgrind, which is not parallel, I would have something like 300 or 400. So good, thanks to Intel for pin tool to have it. NumaProf is based on the old web view of MALT. Sorry, it's not updated with the new one. So it's a bit an oldish interface. So what you get in the graphical interface is some charts like this. For the first touch, are they pinned or unpinned? Meaning, is your thread attached to one NUMA node, or is it a thread which is randomly moving to one or the other when it's touching the first page? Is the memory access local, remote, in green and red, or unpinned? So either because the thread is moving, or either because the page is moving. Yeah, question in the, thanks, Pierre. No. Just not this chain. Can NumaProf this I answered. Are the page size the same across all operating system and CPUs? No. We will discuss that again on Friday. This is 4 kilobytes on most systems, but there is also some huge pages, 2 megabytes, and ARM is using a different page size, which is most of the time 64 kilobytes. Which I have to take in account in MALT, in a NumaProf and MALT. From your experience, is that a lot of work to optimize for NUMA usage? Thanks to NumaProf, no, because most of the time, no. If your code is relatively simple, the main problem is that you miss the Pragma OpenMP on the first access when you make the first touch. If you have a tool to find those location, those parts of your code, this is not, most of the time, this is adding one line. I will show the example after that. This is adding one line in your code. The thing is to see it and to see where to add it. But apart of that, taking care of NUMA is not an easy thing for a complex code which make not a simple grid, let's say. Do you recommend any memory profiling tool for risk? Alors, it depends to profile what. I have no idea here. Sorry, Stevenson. Malt is not working for risk nor for harm because I need to make the port. There is not a lot to do, but I need the time to do it. And NumaProf has no way to run on this. So came back to the tool. You will get also the access matrix, which is saying NUMA node 1 is accessing to NUMA node 1. Ideally, you should get a diagonal. NUMA node 2 should access to NUMA node 2. NUMA node 3 should access to NUMA node 3, etc. If you get a line vertical and only that, it's saying that you are accessing to only one NUMA domain and stressing the link between the CPU. You get also the balance of the pages over the different NUMA domains. Most of the time, you get one which get a bit more than the others. But globally, it should be a bit balanced, ideally. You get also the per thread as format, the per thread view. Which thread is doing how much memory, remote memory accesses, local accesses, etc. to get the balance. Here you see an example where every 4 threads there is a small glitch. Some threads are doing some remote accesses sometimes. We can discuss that if we have time. You get a full log for thread per thread. For every thread, what are the metrics for this thread? And you get the most interesting part of Malt. This is the source annotation, which is saying you, on this line, you are making how many remote accesses, etc. Like for Malt. So I will not lose time. So here I will take an example, which is the CUDA. CUDA, this is a kind of hydrodynamic code done by the CA, so a micro kind of a small benchmark, a relatively small benchmark to test many architecture. At some point, it was there, and I say, okay, I will try to check if it's efficient in terms of NUMA. Me, I was not knowing the code, so this was a code which was unknown to me. So I first tried to run that code without an HBM memory, so just with a standard NUMA node. And this code was showing this example, a quarter of local accesses and 3/4 of remote accesses. So clearly they didn't care about the NUMA. They made it wrong. For the HBM, I will skip it here. I will not discuss that. If you look at the access matrix of this code, clearly we see the problem. The NUMA node 0 is accessing to the NUMA node 0. But the NUMA node 1 is accessing also the NUMA node 1 is accessing to the NUMA node 0. So all the memory is going to one NUMA node. So we are stressing a lot the link between both. And we made exactly, in practice, we can guess that we made exactly the error I was presenting before with the small for loop I have shown. But we need to prove that and to see if we can find in the code from where it's coming. So the first thing to do in that case, it's to use the alloc remote metric to find, the remote access metric to find from where the remote accesses are. What is the loop which is impacting in terms of performance? So here, this is a loop with the mtiles variable, which is using some tiling. And then to search from where the allocation, you can track which allocation, which variable, kind of, is responsible of the remote accesses. So you can come back to the malloc, which has made the wrong accesses. Here it's MC, which is a new matrix 2. And we can know that the initialization is badly done in this class. And if you look, I will not make all the analysis here. If you look deeper in the code following the tool, you will finish to understand that, of course, in this matrix class, I made exactly the case I was showing before, allocating a buffer, filling it with zeros without being in threads at the beginning. So being sequential at the start. So everything got on NUMA node 0. So the fix is relatively simple. It's just to put some pragma OMP parallel to be exactly like you do for the accesses. Exactly the same case I was showing before. So 2 lines. You made a patch of 2 lines in the code, and the performance is increasing from 20% here. Not a factor 2 here because the code was already relatively done and it was a small case, not a big one running. But it was obtained in 1 hour. In a code I was not knowing, which was, I think the code was roughly 6,000 lines of code, something like this. So in a code you don't know, in 1 hour, you are able to gain 20% of performance with the tool in something you don't know. So this is quite relatively efficient in practice. On a more complex code, this is a bit harder to get something, of course. So conclusion about the memory part before we move to the example, the demo effect. Memory is not a trivial thing. You can get a lot of issues in terms of performance. A lot of things you need to understand because this is a relatively complex topic. And even a tiny mistake like just forgetting 1 line at the init can cost a lot during the whole execution. You forget to make a pragma OMP4 in the initialization and you pay the price for the 1 hour running after that. So this is why you need some tools to look at your code and find those mistakes, because otherwise to guess where they are, you are a bit lost in front of the machine. I will stop here and take the questions. Malt is hosted on memtt.github.io, both Malt and NumaProf. Clearly, NumaProf is more experimental than Malt. I maintain more Malt than NumaProf, so I try to keep both running, but this is more effort I put more effort on Malt. So if you have some troubles with NumaProf, please tell me, but clearly it's a bit less stable than the other one, because it's more complex also to maintain. It's harder to implement. Any question before I move to the demo? Maybe remote? Is there a tool, so from Jan, is there a tool similar to LS-Topo for getting the NUMA topology of a machine? Me, I lack a lot LS-Topo and HWLock, so I don't know. You can get it by hand by playing with cat/dev/some directories, but in an efficient way, LS-Topo is clearly making the job well. Do you have any recommendation for profiling for Java? Java, no, sorry. Sorry. For Malt, I question myself if I should at some point port it to Java, but there is already some nice tool for Java, so I don't want to lose my time on this. Also because I'm more an HPC guy and we tend to not use Java for HPC. For NumaProf, no way to get it on Java. It's impossible for me. Recommendation of tools, I'm not doing enough Java myself, so if I give a tool, it will be some from 15 years ago probably, so I will be out. Sorry, Laurent. When using a cluster, are processing CPU bind done by default or only explicitly request? This is exactly what I will show in my demo. No, this is not done by default. I mean, it depends on the job scheduler you have. If you are using Slurm, normally Slurm is doing it. If you are doing some others, it depends. So you need to take care of the binding, of course, when you are in a NUMA architecture. Are these unit test-like ways of catch this memory linked inefficient? Are there some unit test-like ways to catch those memory inefficiency? No, not yet. This is something I was thinking to do, but no, I don't have the time. I don't have the time to make something. But this could be some great work to do to make a library to inject in a unit test part. This can be doable in practice, but this requires some work. So I will move to the demo part. So we have only 20 minutes, so maybe I will do the demo myself. And if you want to play yourself, you have the container at home. Thanks. So if for those who are here, you need to take again the memory Docker, which I used all the week already. So I have several things to show. So maybe I will make the demo myself, and after that you can try to redo yourself on your side. The commands are not very complex. So maybe I can start with NumaProf because I was just speaking about it, and it will be a bit short. So if you go in 6 NumaProf profiling, there is one simple example about NumaProf. I just made a mistake. I just made the solution. So we'll take an example which is exactly the problem I posed before. We have a for loop which is initializing some arrays, and then I'm computing in parallel on those arrays. So exactly the problem I was showing before. I will just show in practice how to get it. Zoom, thanks. I was always saying to zoom, and I don't zoom myself. So terminal, where is my terminal? Terminal. I want my terminal. Yeah. Why I don't get my terminal? Menu, where is the menu? Yeah, I closed it before. So I go to 6 NumaProf demo. I just compiled, make, so simple executable. And NumaProf is relatively easy to use. NumaProf./ the program. Step 1. I will just check there is no one running on the machine. Yeah. I just run the program. So this is a very simple example, so maybe too simple, but I just NumaProf web view, NumaProf, the JSON profile file which has been generated. Here we already have VS Code on the 8080 port, so I need to say to use port 8081. By default, you have an authentication on which is on NumaProf. HP, I said HP 2 times. So the first time you need to set a password on the user. And normally I get NumaProf. So here what I'm saying is that okay, I get the summary of the run. We don't care too much. The cores, how they are spread over the Numa nodes, and my memory accesses, which are all unpinned. Come on. I run on a Numa node. I should see local and remote. No, this is what you expect. Unpinned. This is because I didn't say to my threads to not move. You know, when you launch an OpenMP application like this, if I do that, the threads are not bound to one core, but they are moving from one core to another. So of course, I don't have any Numa binding. So NumaProf is saying everything is random. This is what is in blue. So normally, if you want to bind your threads with OpenMP, you need to say OMP threads OpenMP proc bind. Sorry, I was searching. Equal true. Okay, so it says when the thread starts, it stays where it is at the start. So it makes one thread on the core 1, one thread on the core 2, one thread on the core 3, etc. And they are not allowed to move. So now I can do NumaProf again. OMP proc bind is very important when you are doing some multi-threading with on a Numa architecture, if you take care of the Numa. So again, I will look on the profile. So this time I have 1/3 of my allocation which are local. I have a bit of remote and a bit of unpinned pages because there is still some, and I made a very small problem. So I have part of the executable which is showing some randomness. So I go to the sources, and if I say there is a lot of metrics here, but if I say first all the accesses, I get where my memory accesses the most are done, and I'm going where the intense accesses are here. Yeah, sorry, zoom. Thanks, Pierre. So I get most of my accesses on this line here. Are you share the code? Yes, it is in the container. In the memory container, if you take 6 profiling, step 1 OpenMP basic.cpp. If you go there, most of the accesses are done on those 2 loops, of course, because there is only those 2 loops on the program. And if I put my mouse here, I see that most of the remote accesses are coming from here. And I can get directly all the remote accesses by saying remote accesses, the remote accesses metric. And I get only the remote accesses where they are. So most of them, this is what I will search in my code, where the remote accesses are. And I get all of them which are coming from here. Now the question is why they are remote. I want to come back to which location has made the placement of the memory, has made the first touch. Okay. So for that, I can use directly the metric all first touch or remote first touch. Normally there is one. Where it is. Blah, 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 blah. No, I don't have it. All first touch. Who is making the first touch? So now, who is doing the first touch is done in main globally in this loop. And here we see that it's making all the touch in a loop which is not parallel. Okay, so we found directly what is the source of the placement of the memory. I can get also what is the memory allocation which is responsible of this problem. Sorry, the metrics I need to improve a bit. All the alloc first touch. What are the allocation which are responsible of the remote accesses? Alloc remote. All the allocation which are responsible of the remote accesses. I get directly the data variable. So from that, I can guess what I need to do after. You need to understand your code at some point. No, I don't tell you what to do, but you find directly what is the variable and where the first touch is done. From that, most of the time, you can fix. So of course, here the fix is quite simple. I will need to put again the pragma of MP4. Yes, pragma of MP4. I will compile again, run again NumaProf. And open the graphics interface. 19. And this time, normally, I should have a bit more green than before. Still a bit of red. If you have just a bit, it's not a problem because you can still use the link a bit. It's there to be used, but you need to not stress it. Why is there some green, still some red? This is because I said the placement of the data is done by pages, so by size of 4 kilobytes. If your accesses are not multiple of this size, you might be a bit aside of 2 pages for your threads, which let you some remote accesses. Sorry, there are some questions. The memory access graph is unchanging for me with OMP procbind. Are you running on a NUMA architecture, Joseph? If you do ls2po, you have two NUMA nodes or not? If you have huge pages also on your system, probably it can be a problem because my problem is too small. If you have some data shared along all the processes, is that better to duplicate or to copy? If you have some data which is used by all the cores, sometimes you have some data which is used by all the threads. Then two things, either you make one copy per NUMA node, this is more efficient, but consume more memory and is a bit more complex in your code. If it's not used too much, it's okay to have some part of the remote accesses. You will have some remote accesses. If it's not too heavy on that array, it's fine. If it's become too heavy on this array, then you need to duplicate. I hope it's answered, Luca. Joseph is asking a question again. Just maybe while the question is arriving, I can say that NumaProf is also capable of making some emulation if you don't have a NUMA node on your hand, because you maybe on your laptop you don't have a NUMA, of course. You can emulate a NUMA architecture with NumaProf. So it will be a bit less strict in what it's saying at the end, but you can say NumaProf-O emulate semicolon column NUMA equal, and you say the number of NUMA nodes you want, which will be a multiple of your number of course, but you can emulate 2 or 4 NUMA nodes on your laptop with that tool. Joseph, yes. So if you are on a laptop, you need to use this option -o emulate dot NUMA equal to or the number you want, which should be a multiple of your number of cores. A divider of your number of cores. I was wondering if there is a good learning resource for RISC-V processor. I think most HPC aren't RISC-V, but it's fully open. Yeah, for RISC, myself, I don't have any experience on this architecture, so yes, it could be very interesting. For NumaProf, at some point, I would like to have the support of Dinamorio. This is the equivalent of Pintool, which supports ARM also, and x86, and which is open source. It would be very great if someone can make the port. Myself, I don't have the time to do it. So sorry for RISC-V. Yeah, this is a bit harder. But it could be very interesting and a very interesting thing. I don't have the time to show. We can pass NumaProf on Grayscott, on the Grayscott example I was showing. With the OpenMP version, you will see that I have made exactly the same issue than what I presented here. I didn't make the initialization with NUMA by default. But I can show you the performance difference on Grayscott, because we play a lot with this example during the school. Just by running, I will not show the, if you want to profile it, you can play. I will compile. Make -G8. So on the processor I'm on, I have a very big cache. So if you fit in the cache, of course, you don't care too much about the NUMA because you are in the cache. So I will run with an 8K image instead of the standard HD1. So -R, let's say it's 8K. -O OMP. So I will run by default like this, and I will pin OMP proc bind equal true. Otherwise, I will have my threads moving everywhere. So not taking care of the NUMA. Let's put a grep real time. Maybe I need to short it a bit. Yeah, well, it's okay. While it's running, we can take a question. I can see Malt is capable of profiling MPI application. What about NumaProf? NumaProf, same thing than Malt, but again, you will get one profile per MPI rank. Same way, this is NumaProf -MPI, and you get your profile named by dash number of ID of the rank instead of the PID. So I have 32 seconds. And now I can add the option --NUMA, where I just take care by making one computation just after the memory allocation, same way than the threads will access the data later. So if you look in the code, you will find there is a, if you search the NUMA keyword in my implementation, you will find a location where I just call compute with just after allocating the arrays. For nothing, I will trash the data, but just to compute the same way, I will compute later. Dash dash numa, I put it in a grep, so this is not okay, of course. So remember, we had 32 seconds before. Already we see in terms of cycles, it's a bit faster, roughly a factor 2. I don't know if I will have a factor 2 with the final time, but who guessed the time? 27. Not so good. But on this machine, I need maybe L1 blocking to stress it a bit more. The problem is that this machine has 128 megabytes of L3 cache, so I'm not too much out even in 8 with 8K. So I need to stress it a bit more. So we'll try to go a bit faster. But already we win a bit. 5 seconds. 5 seconds for 2 lines I did in my code. This is cheap. In some cases, you can get worse, because here I'm not making an heavy computation for such a processor. 24, and if I remove the NUMA, it accelerates at some point. Yeah, at some point probably also you have seen it accelerated at some point. It was slower at the beginning and then it accelerates. This is because probably they put the last version of the kernel. The recent kernel, they are able to understand that one page is badly placed and to move it automatically after a certain time. But you see that there is still a price. I'm losing 5 seconds in my run. After a certain time, the page is automatically moved because there is too many remote accesses. The operating system does something, but late. So I will stop here. Maybe I can show you where I make the initializations if I find it shortly. This is if you want to search in the code. So sorry, I zoom a bit too much for myself. CPP, SRC, lib, simulation, and the initialization of the simulation. And here I have, if tuning parameter is NUMA, I just call compute. And I win 5 seconds. That's relatively cheap to get it. Okay. So NUMA is not something easy to have, but if you have a code relatively well done, it's relatively cheap to get right. If you have contiguous arrays, etc. If you start to have some structure with random access everywhere, this starts to become very hard. So I will stop here for NUMA prof, and we will go to Malt. So there for Malt, I have some example also in the 5 Malt memory profiling, which I will compile. And we will have 1 minute if I want to be on time. So I will just make one example. ./step basic, for example, or take a problem. Which one I can take? More basic. So I just malt / my program. It's running, making the profile, and I open my profile, malt-webview -p 8081. Sorry, here I don't know why. For those on the cluster here, you need to add also the IP address you want to listen on. I don't know why localhost is not running. /malt. So if someone wants to run it, I will put it in the Discord. So here the authentication is a bit different. It's like VS Code. You get a token, which you need to copy in the web interface. It's better done than NUMA prof, which has a kind of poor way. So I put the token and I have access to my interface. So here we see the independent. Yeah, we'll zoom. This is a good. This is an interesting thing also when you have a web page, you can zoom when you make a presentation. Where we have seen yesterday with VTune, you have no way. You can see here the summary. So this is a very simple example, which is using a very small amount of memory. You have the command you run on, the malloc you are using, which malloc you are using. If you are using gmalloc or tcmalloc, it's printing here which one you are using. There is one feature I want to add at some point also is to tell you automatically which allocator you should use. I have some prototype, but I don't yet merge it in the main branch. The metrics. So as I was saying, there is some warnings here. The warnings sometimes can arise on small numbers because I also look how the numbers relate all together. So if some numbers are big compared to the next one, I can get up some warnings even if they are small. So this is a limitation of what I did. And if you put your mouse here, you get some information on why I put the warning. You get some domains. What is happening in the C domain, what is happening in the Python domain. When you are using a Python code, you can see both to understand what you are doing. In the map domain also. And you get a summary of the top 5 functions for the most interesting metric of the tool. So here the allocation count, who is making most of the allocations of the code in terms of number. And you can click on it and get directly on the source code. Sorry, here I need to reduce a bit. Directly on the source code, which line is making all the allocations. If I go on something more interesting, the leaks, I have some leaks. What is the top function making a leak? I click on it. And here there is a leak. Sorry, there is a problem offline because I compiled in O3 probably. The leaks is here because I allocate a pointer and never free it. The last loop. You can see a lot of things, probably the peak, global peak, who is consuming the memory at peak. This is using CPP new. Here I have a big array which is allocated, a big 8 megabytes. You assume this is very big. And you can click here and get the details about this 8 megabytes. So the allocated mem in total is 8 megabytes. The local peak is 8 megabytes because there is one allocation of as there is only one, 8 megabytes to 8 megabytes in terms of minimum and maximum. There is also the lifetime, which currently is given in cycles, million of cycles most of the time. So if you are something larger than 1,000, it's okay. If you are something lower, it's a problem. As I said, you have the call tree. Maybe I can take another metric which presents a more interesting call tree. I have a crash. I crashed it. No. Why I lose it? So in the call tree, you can click on one function and go down in the tree. So here it's a very simple example. So everything is green, is red, but you get in blue normally the part which is not costly. You can right-click on it and go in the source code directly from this point. You can zoom with the mouse also. As I said, there is a timeline. Here there is a lot of chunks which are allocated, then all freed in some kind of phase. There is a lot of allocations in terms of rate, amount of memory allocated over time at the beginning, then nothing. It's a good application, kind of. In terms of number of allocations, there is a lot of small allocation done all the time in phases, sometimes free, sometimes alloc. I see that directly. Allocation sizes, here I have the graph I have shown before. Here, most of the allocation were 24 bytes allocation. You get it in histogram depending on how you want to plot it. And how they are distributed over time. You can see that the sizes is increasing a bit over the time. the size of the allocation is increasing over time on this function. And you have the lifetime over size. Normally, you should never get something here, which is having a large block with a short lifetime. Here, I have some examples about this, but we will not have the time to use them. Global variables, as I was saying, you get global variables. Your buffer is one of the top global variables with 64 megabytes. Sorry, this is very big for this program. This is the top one, and you can go to the sources directly to find it directly in the source code. The TLS, you cannot go to the source code. I don't yet have a way to find from where they're coming. I'm still searching a way to make it. You can see also that this buffer, which is 64 megabytes, has been used only on 4 kilobytes, meaning that only the beginning of the array has been really used. So probably I can reduce the size of this variable in practice. And again, you get buffer and a thread private buffer, which are the most used variable in this chart. And here we see in blue the variables and in red the TLS. Yeah. You can get them also over the binaries. By this is here. You can see, you can know from which library it is coming, if it's your program or the library which is giving the memory cost. Here you can get, you need to activate some F instrument functions when you compile your program, but you can also get the size of the stack, the memory used by the stack. This is very experimental and not really perfect. There is still some glitch with this part of the tool, so I will not rely on it yet. And again, the threads, as I was saying, here I have only one thread making all the free and all the allocs to get my application. So we are at the end, so we'll not show more on this demo. If you want to play more on, there is many examples in the directory. You can play and try to find the problems which are in the code. There is also some Python 1, which are a bit just some examples I started to have. Is there some questions on? I can see Malt is capable of profiling MPI application. MPI plus 6, yes, it can do because I do MPI. Do the operating system help us for NUMA? Yes, because it tries to guess what you need. This is what I'm saying. When you make the first touch, it tries to follow where you are. But in some ways, it's making it in a indirect way, not explicit. So this is a problem for you because you did not notice. And if you are not an expert up to today, probably you never know that it was taking care of that for you. And yes, it's helping you because nowadays the operating system is capable of moving the page if it's badly placed. Sorry. So in some ways it tries to help you, but then the problem is, as always, it's everything is implicit. So now if you make a mistake, how you understand that you make a mistake is a very hard thing about the NUMA, because you have no good way to profile in practice. I say no good way, this is not totally true. You have some hardware counter to detect that you are making some remote accesses about NUMA. So you can with perf or vtune get some numbers like this in a real run. And this hint on memory bottleneck can help to optimize the program on bare metal. But yes, NumaProf, every time I pass it on an application, I was able to see some mistake and to improve something. So the tool is clearly useful when you really want to make NUMA. And every time I have seen something when I pass it on a code. Because even if you take care, you necessarily made a mistake somewhere at some point. Maybe we can stop here. There is a question. Yeah. The microphone is. It's on. Oh, okay. Yeah, go.
Okay. I have just one question. What's the key difference? What's the key difference between Malt and NumaProf and the one that the vendor are providing? Like, how do we choose to go for Malt or NumaProf instead of go for the one for NVIDIA, for example? And my second question is, if you can provide, because in the README we don't have all the command that we should use to compile the sample, if you can provide in the Discord, so that you should be able to also try at home. Thank you.
So first question, MALT, clearly this is to understand what you do with mallocs, the dynamic part of the memory management. So this is the goal of MALT, everything which is below malloc. Or if you have a program which is consuming too much memory, you want to know from where it's coming because you are going to the swap, MALT is useful. There is also some options if your program is swapping to dump the profile at, before the machine is starting to struggle. NumaProf, clearly this is for the Numa accesses. So if you have a Numa machine and you want to check the accesses, Numa is a good tool. Compared to vTune and Advisor, as I'm saying, MALT, there is an equivalent in vTune with less metric. But vTune is for Intel only, for x86 only. MALT is open source, so this is possibly an argument also, contrary to the Intel tools. I provide more metrics for the memory management part in MALT than the others. It's running also remote with the web interface, which you don't have with those tools. So clearly, when you are running on a cluster, this is very efficient. NumaProf, I don't know some equivalent tools in practice, which are visual to find from where your problem is coming, and which is a theoretical validation also of what you are doing. Because you have the hardware counter, which tells you where the, how to say, in vTune, with the hardware counter, with perf and vTune, you will get from where you are going to make the remote accesses. But you have no way to find from where they are coming in terms of allocation and first touch. To link both, you have no way in perf. NumaProf is giving you the answer. So it's, in some ways, it's making one step forward compared to those tools. AMD, I don't know what they have with what is their tool, MicroProf. I never used them myself, so not recently, so I don't know where they are with that. I know they progressed a lot, but I cannot compare myself with that. The second question was, sorry. The commands, I think there is a README normally. Otherwise, I can make one, so it will be easier. I forget if I wrote the README in a... There is a README, but I don't know if I put all the commands inside. README. No, I just say I can update the README and update the thing for the end of the week. If for tomorrow, ideally. Okay. Any more questions? Everyone tired? Tired of memory, about memory? So no memory today. Tomorrow, I will not be there with memory on Friday. Okay, thanks. End of the today's session. Thanks for everyone. Thanks for the questions remotely. Thanks everyone.
The auditorium is big, so. Okay, thank you everyone for attending this day. So we'll do a lot more trick tomorrow with Cocos. So on GPU, on the CPU, so to start, and then on GPU next week, and then we will do some wizardry with precision, as mentioned before. So hope you enjoy the day. So see you tomorrow with the new stuff. And thanks also for all the satellite sites, as always. Thanks also for the sponsor, because we need to talk about the sponsor sometimes. And see you tomorrow. Bye.